That's very cool.
3, 2, 1. Yeah, a guy named his online Twitter or his Instagram handles TGT Studios, and he makes these. I actually had one made for Elon. Elon Musk loved it too, so we made him one with. He made one with like this very beautiful red wood.
Yeah.
And what are those things made out of, Jamie? Some diodes or something?
Nixie tubes is what
Nixie tubes.
So they're valves, right? They're old valve technology.
Yeah, he has to get them from Russia. That's he has them delivered over from Russia, so they might have like listening devices implanted in them as well. Yeah. So, Brian, good to see you, man.
Great to be back.
Yeah, great to have you back. So, tell me about this tour that you're doing.
It's a world tour.
Try to keep this sucker like a fist from your face. There you go.
How's that?
That's perfect.
Yeah, it's a world tour. Starts next week in the UK. And then we go everywhere from the South Island of New Zealand all the way to the Arctic Circle, to Svalbard, which is the furthest north that you can go on a commercial aircraft.
Wow.
In the middle, we're in the States for a month, mainly in May. And it's about cosmology and about the questions that cosmology raises. So if you're interested in the science of how did the universe begin, even questions of what may have been there, is the universe eternal? Is there such a thing as before the Big Bang? What is the future of the universe? How does complexity emerge spontaneously in a universe? I mean, we sort of take it for granted that there's a Big Bang and it's all hot and there's just this kind of hot glow of stuff. And out of that, spontaneously, in 13.8 billion years, you get something like the Earth with a civilization and life on it. So how does that... Do we know anything about that? I mean, we do. I'm asking the question rhetorically. We know quite a lot about it. So it's really about showing the size and scale of the universe, but addressing those questions that I think everybody has about what does it mean to be human, this tiny little finite life that we lead in a possibly infinite universe. How do you make sense of that?
Well, it's incredibly exciting to me that there's a giant audience for this, and that what Neil deGrasse Tyson had been doing and what a lot of public touring intellectuals are doing now. They're doing these giant theaters, and these people are coming out to see these shows, and we're realizing that I hate to use the term market for this, but there's a demand for this, and there's a lot of people who are incredibly fascinated by this, and it's spreading information, it's spreading knowledge.
Yeah, I mean, it's in the UK particularly. I mean, Wembley Arena, for example. You know, you're talking about 10,000 people, 12,000 people in these shows. And you're right, they are coming. Although they're big shows, spectacular screens and all that. They're coming to think. They're coming to hear about what we know about the universe and nature. And I think I'm not surprised people are interested, because these are questions that everybody asks. Just why am I here? Everybody's sat there asking that question. But my point is that there is a framework. There's a framework of knowledge. There are things we know about the universe. So it is true that scientists are not going to tell you why you're here. They're not going to tell you what the meaning of life is. But there is actually there are things you need to know if you want to start to explore those questions for yourself. I mean, you need to know that there are 2 trillion galaxies in the observable universe. You need to know that the Milky Way galaxy has got 200 billion stars. Most of those stars now we know have planetary systems. We estimate there are something like 20 billion Earth-like planets, or potentially Earth-like planets, in the Milky Way galaxy alone. So if you're asking questions about what is my place in the universe, you need to know those things, first of all. It's a framework within which you can think.
When you get to those numbers, when you're talking about trillions and billions and all those zeros, my brain just goes numb. There's this lack of comprehension that I'm well aware of. Like, those numbers get thrown about, I go, 200 billion. And it's just...
I think everybody does. I think every scientist, no scientist can picture that number. I mean, even the small number, 200 billion, which is the number of stars in one galaxy. And then when you say 2 trillion galaxies, that's... I challenge anyone to be able to picture that, but it is the reality that we've observed. We haven't counted all 2 trillion, by the way. We have a thing called the Sloan Digital Sky Survey, which maps the positions of galaxies. So you know how much of the sky you've surveyed, and you know how many galaxies you've counted, and then you can spread that across the wider universe, and you get this picture of a vast and possibly infinite universe. I mean, we know that the universe, or very strongly suspect that the universe is much bigger than the piece we can see. So we have good reason to think that's the case. Whether it's infinite or not is another question. And then that goes to your, can you picture infinity? Well, no one can picture infinity. There's a weird thing as well about, we say the universe began 13.8 billion years ago. So that's a measurement. So because we can measure the speed that all the galaxies are flying away from us, essentially. And then you can run time backwards, if you like, to find out when they were all on top of each other. And so it's quite a simple measurement, and we've done that. So we say the universe began 13.8 billion years ago. But actually, all we know really was the universe was very hot and very dense at that time. And we have some theories that the universe was in existence before that, and perhaps some sort of circumstantial evidence. And that means that actually the universe could have always been there, eternal. And when I talk to people sometimes, some people get upset about that. Some people would rather it had a beginning. And the idea that it might have been around forever is more frightening somehow than the fact that it began. And it's interesting the way that people's minds work. What terrifies you the most, an eternal universe or a finite universe?
Yeah, they're both incomprehensible. The eternal universe, if there was an eternal universe, does that negate the theory of the Big Bang, or does it mean that there's a constant cycle of Big Bangs and then expansion and then recompression? Or
yeah, it could do. So those theories are back in vogue. Some of those theories are back in vogue again. So yes, some of them say that there's a cycling universe. So the Big Bang is an event when space gets very hot and very dense and filled with particles. And that may happen again. Or some of the other theories, there's a theory called eternal inflation, which is a theory that, and it's actually the most popular theory, I think, at the moment, for what happened, but why the Big Bang is the way that it is. Because it's got some very special features, the Big Bang, which we could talk about. But inflation is the idea that space-time was around before the Big Bang, and it was expanding extremely fast. And there was doubling in size in the most popular of these theories every 10 to the minus 37 seconds, which is 0.00000 with 37 noughts, 1 of a second. So it's an unimaginably fast expansion. And then the idea is that draws to a close, so it quite naturally sort of dies away and the expansion slows down. And all the energy that was taken, that was causing that expansion, sort of gets dumped into space and heats it up and makes particles, and that's what we call the Big Bang. And those theories, the slight extension to those, say that slowing down just happens in little patches. So most of the universe, the overwhelming majority of the universe, is still inflating at that insane sort of speed. And just little patches stop, and they're Big Bangs. So you get multiple universes, a multiverse. It's called the Inflationary Multiverse. And we are in one of those bubbles. And that's one of the more popular theories.
That's another one. I mean, right now, I'm aware of what you're saying. I can sort of visualize it in some sort of a graphic form, but it's incomprehensible. Like my mind doesn't have the capacity to expand this sense of distance and size to that grasp. Is this because of just the way we evolved? We evolved here on Earth to deal with the space that's in front of us, and now over the course of industrial civilization and education, we're now grasping these concepts that are so alien to the reality, the tangible reality that we exist in every day.
I'm sure that's right. Even very simple things, like you go back to the Greeks, so Aristotle and the great, very clever people, but they thought the Earth was at the center of the universe. Why? Because it feels like it's at the center of the universe. It feels like we're not moving. And that's quite a deep point, actually, in physics. It's like, why is it that we're flying around relative to the sun very fast at whatever speed it is, 18 miles a second or something like that, and the whole solar system is going around the Milky Way galaxy and so on. But why is it that we don't feel it? And the Greeks quite naturally said, well, because we're at the center of the universe. They also said everything falls towards the Earth, so therefore the Earth must be at the center. It's natural.
Right.
And actually it's quite a deep thought to understand why it doesn't feel that we're moving. You have to go all the way to Einstein, really, for someone to take that very seriously. And he said, well, this... there's a great little explanation in Stephen Hawking's Brief History of Time about this, that the idea that you can't tell whether you're moving or not demolishes the notion of absolute space. So if we think about space, if I said space to you or most people, I suppose, you'd think the way that Newton did, of a big box within which things happen. And that's got to be, that's a natural picture of space and the universe, isn't it? It's a thing in which all the planets and galaxies are placed. But in the brief history of time, Hawking says, well, imagine bouncing a ball. So we bounce a ball on the table now, a tennis ball. So I drop it and I catch it again. So let's say I drop it and it takes a second to bounce up. So in that second, the Earth has moved about 18 miles or so in space around the sun. So you could ask the question, did that ball return to the same place in space or not? And the answer is, you can't answer it. It does from our perspective, but from the perspective of someone watching the Earth go all the way around the sun, when I caught it again, it had moved 18 miles. And then from some other perspective, it would have done something else. So the point is, you can't say this is a point in space. It came back to the same place, because that just depends on your perspective. Depends on whether you're watching the Earth go around the sun or whatever it is. So Einstein said that means there's no such thing as absolute space, which kind of follows if you think about it. But that's a difficult, it's a cool but difficult thought process.
Right. I mean, that's essentially what's happening when you're on a plane. I mean, if you're throwing a ball up in the air and catching it on the plane, it's happening at a much smaller scale, right?
Yeah. I mean, you're flying at whatever, 600 miles an hour relative to the ground.
But it doesn't seem like it when you're sitting there.
Yeah, and Einstein elevated that to a principle and said, if you're moving at if you're not accelerating, you're just moving at a constant speed in a plane, or now. I mean, that's essentially what we're doing now. We're moving around the sun at effectively constant speed. Then you can't tell. So there's no experiment you can do. We could look at the decay of a radioactive nucleus or some electricity and magnetism, or bounce a ball, have a pendulum, whatever it is. And there's no experiment you can do to tell you whether you're moving or not. Therefore, that concept has no meaning, because you can't measure it. And that's led Einstein to relativity. Wow. So that's the basis of general relativity, which is our best theory of the universe.
Now, why is it that we think that the known universe is larger than we can observe?
Well, one point is that it's expanding, and we always see the same radiation out there, so the glow of the Big Bang. But there are some deeper reasons. That one, from the theory of inflation, the best way to explain the universe, the properties that we see, is that it's very much bigger than the piece we can see. So, for example, we measure space to be what's called flat. I don't even have to say what's called flat. It is flat. So if you imagine slices of space, let's imagine slices of them at different times. So you just slice the universe and say, there's a big sheet. It's like this table.
Okay, like a table.
There's a sheet of space, and there's another sheet, and another sheet. And it can have a geometry, right? It can be flat like a tabletop, or it could be curved like a sphere, or it could be curved in the opposite direction, sort of like a saddle or a bowl. And we can measure that. And when we measure it, we see it's absolutely flat. And that's a very unusual thing for it to be like. It requires, because what Einstein's theory says is that the shape of space, that the curvature of space is determined by the stuff that's in it. That's basically Einstein's theory of general relativity. Put stuff in space and it curves it and bends it and warps it and stretches it and so on. And what we find is that there's precisely the right amount of stuff in the universe to have a completely flat universe. And the explanation, the most favoured explanation for that, is the universe is way bigger than the piece we can see. And so it's like looking at a piece of the Earth. If you look at a little 1 mile square of the Earth, right, then it's flat, right? You have to look at big distances, kind of order the radius of the Earth, or not, bigger than 1 kilometre anyway, or 1 mile, to see that actually you're on a curved surface. And that's one of the ideas about the universe and why it appears to be the way that it is, because it's way, way bigger. So we're just looking at a little piece, and that's why it looks flat. And that's one of the ideas.
Now, when you say flat, like that, my brain doesn't understand this. Because from our perspective, when you look up at the Milky Way, you see all these stars all over the place. So if you're saying flat, like how much height and What are you saying
so
in terms of like the way to measure it?
The best way to think about it is not to think of 3 dimensions of space, because then we can't picture it.
Okay.
But you can think of 2, like this tabletop, and that's all right. We just forget the other one for now. And so you know what flat is on this table. I mean, you could define it. So you could say, for example, that if I draw a triangle on the top of the table, then all the angles add up to 180 degrees. So that actually defines flat. If you did that on the surface of the Earth with a big triangle, then the angles wouldn't add up to 180 degrees. Or you could draw a circle and say, what's pi? So pi is the ratio of the circumference of a circle to its diameter. That's only true on a flat surface. It's different if the surface is curved. So you can define flatness.
So when you're saying flatness, what is the height and what is the width? Like if you're talking about it as if it's a table, there must be some sort of there's a dimension to it, correct?
Oh yeah, there's a third dimension of space,
right.
But the same applies. It's just a generalization of geometry then. So you can the point is we can picture it in 2 dimensions, but you can draw. You can quite literally, you could imagine sending light beams out, and we do this measurement actually. We can look at the most distant light we can see, which is something called the cosmic microwave background radiation, which is if you imagine looking out. If you look at the Andromeda Galaxy, which we can see with the naked eye here in LA, you can see that. It's the most distant object you can see with the naked eye. And it's about 2 million light years away or so, which means the light took 2 million years to get to us. So it's a long way away, but it's very big. So as you look further out into the universe to more and more distant galaxies, you're looking further back in time, because you look at something that's 1 billion light years away, then the light took 1 billion years to get to us. So you see it as it was 1 billion years in the past. And we can actually look so far out that we can see almost back to 13.8 billion years ago, which is very close to the Big Bang. So we can look to light that began its journey before there were galaxies. And that's the oldest light in the universe, which is, by the way, one of the pieces of evidence when people say, I don't believe in the Big Bang. The answer is, well, you can see it. So it's just there. You can see it. We have pictures of it. That light, it turns out that there are sort of structures or ripples in that light, which we can use as a ruler. So quite literally as a ruler on the sky. And then because that light's been traveling through the universe, we can see how that ruler has been distorted as the light has traveled through space. And so we can infer whether space is flat or curved or how it's warps, if you like, just from that measurement. So it's a beautiful measurement. Is
it possible that in the future we'll be able to see past 13.8 billion years?
Not with light.
Not with
because
light.
What the picture is that before, it actually was released 380,000 years after the Big Bang. It's a very precise number. You might say, how do you know that? Well, before that time, the universe was so hot that atoms couldn't form. So you had a soup of electrically charged particles. It was just too hot for electrons to go into orbit around nuclei. So the universe was opaque to light. So you just couldn't. It was like almost like a big glowing star, if you like. And then when it was expanding, it cooled past the point where the atoms could form. And at that point, it becomes transparent, really almost instantly in a cosmic timescale. And so the light could then travel in straight lines through the universe, and we can see that light. So we see the light from that time, but further back than that, it's opaque. So you can't see past that with light. But you can potentially with gravitational waves, which is this measurement that got the Nobel Prize a couple of years ago, the LIGO experiment here in the United States. And that looks for ripples in the fabric of space and time. And in principle, if we had a big enough detector, you could see the ripples from the Big Bang. So you could take an image of the Big Bang in gravitational waves, which would be, but you need an enormous sort of space-based detector that we're not going to build anytime soon.
Now, obviously, this is all through equipment and technology that's been invented over the last few hundred years and perfected. Is it possible that things could get better and you could get some ability to detect things even in a far more distant way?
Yeah, I mean, gravitational waves are incredible. I mean, Einstein predicted them in 1915. Never thought they'd be detected because you need such a high, you need lasers. They didn't have lasers. But the thing, LIGO, this experiment, which is half in near Seattle in Washington State and half in Louisiana. So they've got 2 detectors. And they're basically sort of, I don't know, 3-mile long laser beams that just sit and measure the sort of stretching and squashing of space as the ripples in the fabric of the universe go through. And what they've been observing are collisions of black holes. So you can imagine how extreme, like a colliding black holes. It's an incredibly extreme event. So it shakes the fabric of the universe, and the ripples come across the universe. And these laser beams, which are just basically rulers, can detect it. They just sort of ring almost like, just vibrate as the ripples go through in space and time. Kip Thorne got the Nobel Prize last year for this. He's one of the greatest living physicists. So I once saw him describe it as a storm in time. So you've got a time storm. It's a beautiful image. So that technology is incredible because the change in length is, I can't remember the exact number, but it's way, way, way less than the diameter of an atomic nucleus. So the change in length of the beams, it's tiny measurement, but we can do it.
So this a collision of black holes, the idea that you can detect that.
Yeah.
Yeah.
The paper, the first paper they published, there are 2 black holes, and they were about 30 times the mass of the sun each. And they were orbiting each other and spiraling in towards each other. And they accelerated. At one point, they were approaching each other at 1/3 the speed of light. And they accelerated to 2/3 the speed of light in 1/10 of a second, and then hit each other. And the explosion, the energy release was, I think I'm right, it was something like 50 times the energy release that the power of all the stars in the observable universe glowing. And it was something like 50 times that amount of energy for a tiny fraction of a second. But it's an unimaginably violent event. And that's why our detectors can see the ripples that makes in space and time. And we detected, I can't remember, it's 2 or 3 of them now, and also 2 neutron stars colliding. We saw that as well with it. So it's an incredible machine, which is why it got the Nobel Prize.
Now, there's a supermassive black hole at the center of every galaxy.
Yeah.
But there's also other black holes that aren't necessarily in the center of galaxies.
Yeah, so these little ones, little. They're a few times the mass of the sun, and they're from collapsed stars. So they are stars at the end of their life, very bigger than the sun, more massive than the sun, but they run out of their fuel and they start to collapse because gravity squashes them. And if they're sufficiently massive, then there's nothing that can stop the collapse. And so they collapse, as far as we know, to a point, right? Essentially an infinitely dense point. We don't really know what happens we don't know what happens right in the middle. But they collapse to such an extent that there's a region around it from which light can't escape. And so nothing can escape. And that's a black hole.
And what happens to them? Do they travel? Are they moving through space?
Yeah, they're still stars,
right?
So they're still there. They're surrounded this region where if you fall in, it's called the event horizon, and if you go across that horizon, then you are going to the center. There's one way of thinking about it, which is quite cool, which is that the time and space sort of flip is one way to think about it. So in the same way that we are going into the future now. So we're going to tomorrow. There's nothing we can do about it. We are going to tomorrow. In the same way, if you fall in across the event horizon of a black hole, you are going to the middle, the singularity it's called. So that's your future. Every line of your future points to the center of the black hole. So it's kind of the ultimate of no escape, the ultimate prison. You're going to get squashed to an infinitely dense point.
Not every star becomes a black hole at the end of its life?
No, because if something like the sun,
we have a small star.
It's quite small, yeah. And when it collapses, there's a sort of a pressure, a force, if you like, which is caused by the fact that electrons don't like to be very close to each other. So it's called the Pauli exclusion principle. But essentially what happens is that, so as they get squashed closer and closer together, they move faster and faster to sort of get out of each other's way, if you like. And that makes a force which holds them up. And so that creates what's called a white dwarf star. So you can have a blob of matter. They're about the size of the Earth, but they're about the mass of the sun. And so that's for smaller stars. They end up as these white dwarf things, which are very dense objects. There's another version, which is called a neutron star, which is the same thing, but for neutrons. And they move faster and faster. So if it's massive enough that it overwhelms the electron thing, then the electrons sort of crush into protons and turn into neutrons, and the whole thing starts again. And so a neutron star can be, at least 1.5 times the mass of the sun, let's say, but it can be about 10 miles across. So that's an incredibly dense ball of matter held up by the neutrons moving around. It's got a fancy name. It's called neutron degeneracy pressure, but that's what it is. But if you go even bigger, then even that can't hold it up. And as far as we know, then there's no known force that we know of that can hold the thing up if it's too massive. And so that's when it just almost winks out of existence, if you like. It collapses and collapses and collapses. And that's when you get a black hole.
We try to put that into perspective. The sun is 1,000,000 times bigger than the Earth.
Yeah.
And this neutron star is, would you say, 1.5 times the mass of the sun,
so
but 10 miles wide?
Yeah. So, and there's loads of those around. They're called pulsars. So we see those all over the place. The first one that was discovered was called LGM1 because they spin very fast. And it was called LGM1 because it's a very regular pulse, and they thought it was Little Green Men. So they called it kind of jokingly Little Green Men 1. And so, yeah, we've seen that there's one called the Crab Pulsar, which is in the Crab Nebula, which we saw the supernova explosion. So that's when one of these stars explodes at the end of its life and then collapses to form a neutron star. And we saw that in 1054 AD.
Wasn't there some speculation that our solar system at one point was a binary star system, and that one of those stars had become a dwarf?
I don't know.
Someone had read something about that in relationship to the dense object they believe is outside the Kuiper Belt.
Yeah, I mean, there's some evidence. There's a bit of evidence that there's something out there. Yeah.
Yeah.
Because of the periodic extinctions and things on Earth, like you get periodic bombardments from out in the Kuiper Belt. So yeah, I think one of the theories is
periodic extinctions.
Well, yeah. So for example, like there have been mass extinctions on Earth when a lot of the life died, and we don't know what caused all those, but sometimes they're impacts from space. That seems clear. And so, yeah, there are theories that there's something orbiting out there which can disrupt all these objects out in the Kuiper Belt that sends loads of comets and asteroids inwards to the inner solar system and can cause havoc. And so there's some people look at those theories. I mean, I don't know. It's one of those, it is a possibility that there's something out there.
The speculation was that there's something out there. Correct me if I'm wrong. Something called a galactic shelf, like that it gets to a certain space and it indicates that there's something far larger out there.
Yeah, I mean, I don't know the exact about the stellar-sized or mass objects out there. I don't know that. I mean, there are some sort of suggestions. There's another planet out there, a big planet, for example. But you're right. There can be stuff orbiting way beyond the Kuiper Belt, and we're talking, a light year away or something like that now.
It's interesting because it's incomprehensible, the distance, right, in our minds, how far that must be out past what we used to call Pluto. But for whatever reason, that becomes more interesting because it's in our neighborhood. Whereas if they find some distant star system and that it might have a planet that's similar to Earth, that doesn't seem as compelling for whatever weird reason.
No, yeah. I mean, I think the planets around Alpha Centauri and Proxima Centauri, which are the closest stars, it seems like there are planets around those now. And I think that was interesting because we could conceive of going there.
Right.
I mean, there was this idea, Stephen Hawking actually and some others before he died had this idea called Breakthrough Starshot, which is the idea to send a little probe out to the Alpha Centauri system. And I think in their view, Yuri Milner as well, the entrepreneur, wanted to do that. And I think it's something like 100 years travel time or something with our current technology. And they pointed out that we don't do that now. We don't think 100 years in the future. But if you go back when people were building cathedrals, people used to routinely start projects that would take 100 years to bear fruit. Yeah. And so we could imagine going there. And that then becomes fascinating, I think, because then you've got a solar system, another solar system that you could go and visit, conceivably.
Conceivably. Yeah, I mean, what kind of speed are we talking, and how long would it take to get there?
Well, yeah, I mean, so it is. I think the idea was about 100 years to get there. So it's going 4 light years or so in 100 years, so whatever that turns
So you would have to essentially do what they did in like the Ridley Scott Alien film and put people into some sort of a
it'd be a robot probe. It wouldn't be a crewed probe.
Wouldn't be possible for a crew?
Well, it is.
But you'd have to freeze them?
Yeah, that's always, when you talk to engineers, you had Elon on, didn't you?
Yes.
Engineers always say, physicists go, well, it's possible in principle, so over to you. You do it now. There are no laws of physics that tell us we can't do it, so we just do it.
Right.
But, it's...
That's a weird relationship between the physicists and the engineers.
Yeah. But yeah, in principle, you're right. If you can send a little robot spaceship there, you can send a crewed spaceship there.
I'm of the opinion as time goes on and augmented and virtual reality gets better and better that it doesn't really totally makes sense unless we're talking about colonizing someplace to send biological life to another planet. And if we can send some probe that doesn't have to worry about the biology being affected by radiation or by the speed of travel or even by food, we can send something out there and almost be there by virtue of goggles, virtual reality goggles, or something else.
Yeah, you hear that. In science, at the moment, space science, we have this debate a lot, actually, because, of course, space probes like Curiosity that's on Mars at the moment, that's really cheap compared to sending people to Mars. And so quite often the scientists who want to find out about the worlds will say, well, we should spend it on robots. We shouldn't spend it on people. I think crewed space exploration is, in some ways, I mean, it's clearly true at the moment that humans can do more than robots. So we can explore the place better.
For now.
But I think it has to be, it's about something else. I mean, it's about, and it's not only, it's about living and working off the planet, which I think is quite a persuasive argument, actually. We've already industrialized near-Earth orbit. So it's already a multi-billion-dollar industry, communication satellites and weather satellites, GPS, whatever. We're already up there. And so learning to live and work in space is, I think, a natural extension of our civilization. Plus the fact, if you talk to Elon or Jeff Bezos, they point out that the amount of resources available just slightly above our heads is vast. And so I remember I talked to Jeff Bezos actually once, and he thinks really simply, and he said, for example, in the asteroid belt, there's enough metal, I think, to build a skyscraper. What is it? It's something like 800 stories tall and cover the Earth in it, right? If you want. Now, we don't want to do that. But his point was that the energy from the sun is all up there. The resources are up there. So you could almost imagine trying to zone the Earth residential at some point in the future to protect the planet and do your heavy industry off the planet, for example. And it sounds like science fiction, except that now SpaceX and Blue Origin, those people have got reusable rockets. So suddenly the economics become sensible. So I think expansion is good, and I think we will expand, and I think we will expand outwards because there's not much room left on this planet to expand. So I think we'll do. So, but that's a whole different idea. It's not about gathering scientific information. It's about a frontier. And all the benefits that come from operating as a civilization on a frontier, which we've sort of lost on the Earth because there is no frontier left. And so I like that idea that Mars, and when you talk about Mars, especially with Elon, he's right that that's the only place you can go. So there is no other planet we can go to other than Mars. You can't go to Jupiter or Saturn. You can't go to Mercury or Venus. So if we want to go somewhere and expand our civilization, it has to be Mars. And everything's there that you need. So, but that's a different thing to saying you want to find out stuff. You're right. If we just want to find out stuff, then you send robots.
But as far as expanding actual civilization and bringing it to another place, one of the things that freaks me out is people get depressed about living in Seattle. I mean, you're going to live on Mars?
I wouldn't. I agree with you.
Yeah.
It'd be a horrendous thing. It'd be like the Western frontier. It's the frontier when people cross the states.
Yeah,
an incredibly dangerous thing to do.
But when people cross the states, they still got to Wyoming and beautiful places and Colorado and
but it was hard.
Yes.
I wouldn't have wanted to do it.
But once you got there, there's a river, and there's trout in the river, and the meadows are green. And
it's right. I mean, I agree with you, right? I mean, I'm not going to go there till there are vineyards and hotels and things. But however, it is true that there are people who like the challenge. And what is true about Mars, it's interesting actually, because we know something about the history of Mars now, quite a lot about the history of Mars. And it's certainly clear that there was water, almost certainly oceans, rivers. And that water is almost certainly still there. So I would say certainly still there.
Well, they have found large quantities of ice now, right?
Yeah, so there's certainly ice. There may even be pockets of liquid water below the surface somewhere. So couple that with all the minerals and the resources that we know are there, and you have everything you need. So that's the thing about Mars. It's quite nice relative to everywhere else other than the Earth. You can't go to Venus, right? You just melt. It's, what is it, 400 and something degrees and 90 atmospheric pressure.
Yeah.
So Mars is quite nice. But I wouldn't go there. I agree with you.
What's it's not the gravity of Mars in relationship to the Earth?
It's what is it, about a third, I think.
Third,
right? Yeah, something like that.
So it would still have a significant weakening effect. Like if you went to Mars and then somehow or another in the future they were able to get back to Earth, your body would have a real problem with that, right?
It would, but there is still gravity. Maybe it's a bit more than a third. I can't quite remember, but it's something like that. But yeah, so there's still gravity. Right. So there's gravity. There's some protection from you'd probably want to live in the caves actually, or something like that, because there's no magnetic field there, so it's quite a high radiation environment, but not too bad. It's further from the sun than we are. It's not too. There are places on Mars. There's a very deep crater called Hellas, which is a big impact basin, and at the bottom, it's so deep you could fit Everest in it. So you put Mount Everest in there, the summit of Everest wouldn't reach the rim of the crater. So it's something like, I don't know what it is, 7 miles deep or something, 6 miles deep. So you could go there, and at the bottom, the atmospheric pressure is so high that you could just about have liquid water occasionally on the floor of that crater. And so it's quite warm sometimes. It can be 20 degrees.
Really?
Yeah, there, Celsius.
Wow. So better than Minnesota right now.
Exactly.
Minnesota's experiencing a serious cold front.
That's right, yeah. So it can be warmer than Minnesota. And so there are places where it's not horrendous on Mars. So the Martian is kind of realistic in that sense.
Sort of.
Bits of it.
Do you watch those movies and shake your head?
I like them. I like science fiction,
Right.
So yeah, I don't sit there. I grew up with Star Wars. That was when I was 9 years old or something like that.
It's
so I don't
funny
sit there
watching
going,
it
I just
now.
don't. Yeah, I'm not having this. I had an argument with Neil deGrasse Tyson, not an argument, but a debate with him about lightsabers once, because I claimed that they're physically, in principle, they're possible. And he was trying to say that they aren't, but they are.
Would it have to loop back around because the light's not continuing to, the fact that it goes to a certain distance and pauses?
Well, you'd have to have a mirror or something, I guess, yeah.
Something would have to be the end of it, right?
That's true. So it'd be a different kind of lightsaber. The only point I was making is that photons, particles of light, can bounce off each other. So we see that in really high energy experiments in particle accelerators, we can collide photons together. So my point was a bit of a pedantic physicist one, but it is true that light can bounce off it, can hit light,
right? But
very, very high energy.
But when they press that button, it goes to a certain distance.
Yeah. That's engineering.
Right.
No, I agree with you. The distance thing doesn't work. Yeah,
there's no mass to it, right? So as you're swinging it around, you wouldn't have the leverage of a long thing. So why not make it really long? Because it wouldn't be difficult to swing around. Like you could stab someone with a lightsaber a mile away.
That's true. Yes,
right?
True. Well, that's just a laser, isn't it?
Yes. Like why make it so short?
Yeah,
it's ridiculous. You have to swing. You have to be close to hitting a person with it. That's a silly design.
You are picking holes correctly in the engineering part of mine. The only point I was making is the physics is that, which I think is quite interesting, is that light can bounce off light.
Yes.
That's the point.
So, but there would have to be something that causes it to stop at the very end.
Yeah.
Yeah.
Yeah. Which would be, you're right, it'd have a mirror, but it wouldn't look cool, would it, if there was a...
No.
kind of thing with them.
Well, what drives me crazy about Star Wars is not the lightsabers, it's the lasers when they're shooting the guns. I'm like, why can I see that when I can't see bullets?
Yeah.
Like, this is supposed to be way faster than a bullet.
Yeah.
Like, why is it easy to see this? Because it's like, you can duck. You can get out of the way of those things.
They're really slow, aren't they?
They're so slow.
Yeah.
I would be so angry. I'd be like, this is so dumb. I could go warp speed in this Millennium Falcon and travel the speed of light, but for whatever reason, these lasers are so slow that you could duck out of the way of them. That's so dumb.
And it's not only Star Wars, it's everything. Every single film does that.
Yeah.
Yeah.
Why?
Well, it's like films like. Also, I worked on one of these films years ago, Sunshine.
Oh, that was a great movie. Very underappreciated movie.
Yeah, I think so. I think it's a brilliant film. But in that, so they asked me, Danny said, I want to do it right, so I'll do the spacecraft without any sound. So when it's traveling through space, it'll be silent. And it looks shit. You know, just when you watch it, it's the same when you try and film astronauts and they're in zero G and they always move slowly. Mm-hmm. It's like, why? You know, you're right. You don't.
Right, you'd be able to move very fast.
As fast as you want.
Yeah.
But it looks silly. So there's kind of I suppose it's what audiences have got used to over the years. And so in the end, you have when the spacecraft goes fast. Apart from 2001, which didn't do it.
Yeah.
It was silent in 2001.
Well, Kubrick was a stickler for science and he would do complex mathematics in his spare time. What a fascinating guy that must have been.
Yeah. I read that they just someone just found an interview, didn't they, the other day, where he explained the ending of 2001.
I didn't see that.
Yeah, I saw it yesterday actually, and it was kind of a really simple version of it. He just said, well, the super intelligent beings take him in and put him in a zoo, basically, and watch him grow old, and then send him back to the Earth as a super being. No, that's the worst explanation at the end of 2001 I've ever heard. But it was Kubrick's. That's what Kubrick said. So he falls into the monolith. Yeah, they just put him in this room, which is kind of a bad version of a French chateau or something. Watch him grow old and then send him back to the Earth as a super being.
What? Okay.
That was Kubrick's version.
How strange. It's a weird genre, right? Because sometimes people get things right. Like, didn't H.G. Wells predict a significant amount of scientific inventions in the future?
Well, there was his. I mean, it depends which one, doesn't it? There was a moon one, wasn't there? He did a journey to the moon. I mean, his time machine is not
right.
We're not going to be able to do that.
Really worked out yet.
No. but yeah. I think it's. I always like science fiction.
Yeah.
I like Arthur C. Clarke a lot. You know, because I think it is. You're right. It's a form that you can let your imagination wander and address things without restriction. I think.
Did you like the Alien series?
I loved it.
Yes,
I saw Alien when I was at school. It was 1979, right? And we had a school film club. And in the 70s, they weren't like they are now. You know, and so the first films they put on, the 3 films, I was 11. And it was Alien, Apocalypse Now, and Life of Brian.
Wow.
So that was my introduction to cinema.
Wow. Well, those are 3 great choices.
Yeah.
But I feel like Ridley Scott's original Alien is probably one of the greatest horror science fiction movies of all time, and one of my all-time favorite movies. But I really like the newer ones as well. Like I like Prometheus, and I really liked Covenant, the last one.
Yeah, Prometheus. I don't know.
It's not the best one.
I
love kind of like what they're trying to do with it. The whole idea about the engineers coming back in time, and
that's why I was disappointed with it, because I thought the setup, the opening is brilliant, and I thought this is just going to be brilliant, and then I thought it just lost its way, and it was a disappointment because it could have been so brilliant.
Yes, I agree with you. Yeah, the beginning was fantastic, but I think Covenant was more exciting, and but it's also preposterous. Like, if you went to another planet, like, the last thing you'd be doing is just breathing in the air, right? I mean, we'd have to be really if there was a life on the planet, we'd have to be really careful, A, not to contaminate, but B, not to be contaminated, right?
Yeah. I mean, there's also, I mean, you know, the other thing in science fiction films is gravity, because you always, even in Alien, you always just say the spaceship's got gravity. Again, there's only 2001.
Right.
Where everybody floats around.
Yeah.
Because, has a spinning thing.
Right. The spaceship has gravity, and then when you land, the gravity is exactly like Earth.
Yeah.
Perfect.
Yeah. but it's
no, it's ridiculous. Yeah, I mean, what are the odds that you would find a planet that is exact? Like, even if a planet was 1.5 times the size of Earth, it would have far more gravity, right? And that's really common for a planet to be like just a little bit bigger.
Yeah.
And then we would be like, fuck, everywhere we'd be walking, we'd be getting crushed, right?
I agree with you.
Yeah.
But I suppose that's not the point. It's about ideas, isn't it, science fiction?
Yes, and this whole idea where you're just supposed to let the story play out and
yeah. Well, I mean, Sunshine was the premise is silly. I mean, the premise is the sun is dying and we're going to go and fix it.
Yeah.
So both of those things, it fails on its first line a bit in terms of realism. But the idea is that it's not about that. It's about the sun as a god in some ways. So it's about our response to the power of nature, and it's about deifying this thing and worshipping it, and how ultimately you go mad. If you remember the film, there's Pinbacker, who's the first captain that went to the first mission to go and restart the sun, which is the mad bit, but then became a religious fundamentalist essentially, and then decided. It's a fascinating idea that he decides that to bring meaning to his life, he will become the last man, the last human. And so he wants to be the last. He wants the sun to die, and he wants it to take humanity with it. And he decides to make that happen. So he stays there, waiting for the second ship. And I like those ideas that, what's your reaction to the power of nature? And this happens in... It's one of the things I do in my shows. I'm not being a commercial person. I've just thought of it. One of the great things about cosmology is that it is terrifying in the truest sense of the word. I mean, we talked a bit about the size and scale of the universe and black holes colliding and those things. It is very frightening, but also the act of trying to understand our place in nature and the size and scale of the universe and our tiny presence within it is valuable. So that you can be terrified but also inspired and interested. And it's part of, if you want to ask questions about what it means to be human and means to be alive, then I think you find the answers in confronting that reality, which is that we live in a terrifyingly vast universe. The powers in the universe that we cannot comprehend, as you said. But that's what you've got to face, because that's reality. So you can't hide your head in the sand and just duck it. And it can send some people crazy.
I'm sure. And it is really interesting that we need that suspension of disbelief in order to sort of make a film on space. You almost have to go, well, this isn't really how it would be, but this is how you have to make it in order to fit it into a 2-hour movie.
Yeah. And then the film, as with Sunshine, becomes about... Then you can have the film about something else.
Yes.
Because it's not really about that.
Well, did you like Event Horizon?
Yeah, I did, actually. I thought that was fun, quite a cool film. Yeah.
Ridiculous.
I haven't seen it for
fun.
years. Yeah.
I always wanted to ask about their concept of propulsion. That almost like space would be flat, and you would fold space over, and you would intersect those 2 points, and you would be able to travel vast distances instantaneously, right? I'm doing a terrible job of explaining it, I'm sure. But is that a concept that people have actually considered?
Yeah, you can, in general relativity. So Einstein's, I should say what it is, Einstein's theory of general relativity is our best theory of space and time. And so it really is, as we talked about before, it's you imagine... space and time as a sheet. Just imagine it as a thing, sort of literally a sheet, a surface. And all the theory says is that if you put matter and or energy into that, then it curves it and distorts it, and it can stretch it and make it shrink. And so it's the response of space and time to matter and energy. So the simplest version will be the sun. So you put a big spherical ball of stuff in there, and it warps space and time such that the nice straight lines, something just travelling, minding its own business through that warp space, turns into an orbit.
And that's why you can actually kind of see things that are behind the sun?
Yeah.
Okay.
So light bends around the sun because it's just travelling through the curved space. The Earth goes round the sun because it's just rolling, minding its own business through the curved space. So an example would be, you might say, well, how does curved space, can that give rise to something that looks like a force, which is gravity? So the best analogy I know of is to think of walking around on the surface of the Earth. So if you stand on the equator of the Earth and you with your friend and you say, we're going to walk due north. So we're going to set off, let's say we're 1,000 miles apart on the equator and we're going to walk due north. And what's going to happen? So you walk in straight lines. You don't change direction. You don't do any accelerating. But the straight lines are the lines of longitude on the surface of the Earth. So as you go further and further north, you get closer and closer together. And if you carry on to the pole, you bump into each other. But nothing's happened. Right? There's no forces acting. It's just that you're moving on a curved surface. And so you get closer. And that's basically Einstein's theory of general relativity. Now, why did I start talking about that?
Event horizon, the idea of folding.
Oh, yeah. So all you have to do, so that those folded kind of geometries, is you have to try and specify where you would put the matter and what kind of stuff you'd put there to make the geometry fold in that way. And you can do it. So you can write down that geometry. So it's called a warp drive geometry, I think it's called. It's in textbooks. So you can do that to have a warp drive. The question becomes, what sort of stuff would you have to actually put into the real universe to make it warp in that way? And it usually turns out that it's the kind of stuff that doesn't exist, right? But it has properties. It's sort of matter or sort of energy that has properties that do not exist in nature as far as we can tell. But you can still write the geometry down in Einstein's theory.
So if you had the significant force or mass or whatever it is, if you had that stuff that doesn't exist, it is a concept that
so the geometry exists. So you can do it, and you can do the calculations, and you can see the warp drive. You can construct wormholes that connect distant regions of the universe, which you could use as time machines. You can do all that in the theory, but in nature, you'd have to have the right stuff to do it.
But that stuff is not real.
That seems to be
as far as we know.
Yeah.
Now, what would have to happen? Like you would have to have enough power or mass to be able to fold those two things together?
It tends to be weird stuff, like stuff that has a negative pressure or something like that. So stuff that has physical properties that are just bizarre, and that no matter or energy that we know of in the universe has. So that to make the geometry happen.
But it's conceivable in theory that this could exist, even though it doesn't.
It's a debate ultimately. So wormholes are a good example. So that would be quite literally, we talked about the surface of the Earth. So you fly to Australia from LA and you have to go quite a long way around the edge of the Earth. Or you could tunnel straight through and get there quicker, right? So that's a wormhole.
Jamie's got a little graphic up there.
There it is. There's a wormhole. So you could go all the way around the edge, or you could take the shortcut. So the question is, so you can do that in Einstein's theory. You can write down that geometry, and there it is. So the first question is, can you make it? And as we said, we don't think that stuff exists.
Right.
There's a second set of bits of theoretical work, which are, if you had a wormhole, then what would happen if you tried to travel through it? And what seems to happen is that they become unstable the moment that anything tries to go through. So you get kind of a feedback of stuff going through and through and through and through. And so it collapses. And there's a great book by Kip Thorne, actually. We just mentioned him. He got the Nobel Prize last year for the Gravitational Waves. And he wrote a brilliant book, I think it's in the 80s, called Black Holes and Time Warps, where he talks about the answer is we don't fully know, but most physicists think that even if they existed, they would be unstable. And as soon as you even try to transmit information through them, send a bit of light through, then there would be this sort of feedback and they'd collapse. And ultimately, the reason we don't really know absolutely is because you need what's called a quantum theory of gravity, and we don't have one. So we don't have the theoretical tools to be absolutely sure that these things would be unstable or don't exist in nature. But we strongly suspect that they don't. If they did, you could build a time machine. So Stephen Hawking wrote a paper called the Chronology Protection Conjecture. And conjecture is the important word. So the conjecture basically was that the laws of nature will be such that you can't have stable wormholes and you can't build time machines.
And if you send something through it, it would destabilize it.
Yeah.
And if it didn't destabilize it, how would your physical body deal with the stress of that?
Well, it doesn't have to be that you can build them. That's called the tidal gravitational force. So it's the difference in gravitational pull across your body, which is one of the things that gets you if you fall into a black hole. So before you actually get to the singularity, you can get, it's called spaghettified as a technical word. So you get, and it's just like the moon's, the tidal effects on the Earth, which are quite small, but they still raise tides on the oceans. So that can be if you think about something like a black hole, that can be a massive difference in gravitational pull from your head to your feet. And so it can stretch you out. And so, but you can, with wormholes, you can write the geometry down in Einstein's theory such that you could go through. So you don't have to be destroyed or anything weird happen to you.
Would you have to have something protecting you, some force, some sort of a?
No, you just literally you fall through. I mean, so if they would exist, you just go through. You sit in a little spaceship, but you wouldn't. There's nothing inherently in them that says that you would be ripped apart or anything like that. But
what are your thoughts on alien life, on life outside of this planet? Is this something you think about?
Yeah, I think there must be. Even in the solar system, I would not be surprised if we find microbes on Mars or on some of the moons of Jupiter or Saturn where there's liquid water.
Like Europa.
Yeah. And the reason is, if you think about, the reason I think that, and it's a guess, is because if you look at the history of life on Earth, then, so Earth formed and it was just there was no life. It was a ball of rock. And almost as soon as it cooled down, we see evidence of life. So certainly 3.8 billion years ago, possibly even further back than that, we see evidence of life on Earth. So somewhere along the line, geochemistry, active geochemistry became biochemistry on Earth. And we have some idea, that if you get gradients of temperature and acid and alkaline and the conditions that are naturally present on the surface of oceans, then complex carbon chemistry spontaneously happens. So we know that life, almost certainly we know that life began on Earth. I mean, the other option is it came from space or something like that, but it probably didn't, right? It probably began on Earth. So that means that at least here, that happened. And that we know that the conditions that led to the origin of life on Earth were present on Mars 4 billion years ago. And we know that they're present on Europa today. So I don't see that there's anything special. Life is just chemistry. And the idea that geochemistry becomes biochemistry is not fanciful because it happened here. So I think that given the same conditions, it would be surprising to me if the same thing didn't happen, in that life begins. So that's one of the, to test that is one of the great frontiers of science now. It's one of the great challenges, which is why, another reason we're interested in Mars, because we know those conditions were there. We know there were what's called hydrothermal vent systems on the floors of oceans on Mars 3.8 or 4 billion years ago. So it would be good to know if what I've said is right. And the way we find out is to find life or evidence of past life.
Are you aware of the speculation that was going around? How recent was it, that Occupy thing, the octopus eggs? There was a group of scientists that were speculating that it's panspermia, the idea of panspermia, that it's possible that octopi had come from somewhere else. Some frozen eggs had actually come from somewhere else and landed on Earth. And these were like legitimate scientists that were contemplating, not morons.
I don't think...
Have you seen this?
No, I didn't. But I mean, I think it's unlikely. So panspermia doesn't have to be unlikely.
Right.
I mean, for example, you might have seen the other day we found an Earth rock on the moon.
Yes.
Right. Well, it was back on Earth now because the Apollo astronauts brought it back, didn't they? It's 4 billion years old or something like that.
One of the oldest rocks ever found.
Yeah.
Right.
So we know that material gets transferred between planets. And so it's not inconceivable that microbes could survive that journey. Right. We know that microbes can survive in space, for example. So that isn't mad. It's probably unlikely, but it's not mad. But with the octopus, I hadn't heard that. But the thing is that the octopus is still extremely similar biologically to us. I mean, the differences are negligible.
Yeah.
So it's still got the same energy system with the single ATP and DNA and all that stuff. It's all very, very similar.
It was something about RNA and DNA. Did you find that article?
I'm looking at a different one from a different website. It's about the same thing. It has to do with the Cambrian explosion. And there were 33 authors on a paper that got published in the Progress in Biophysics and Molecular Biology that talked about this possibility. There are other people that disagree with it, though.
Right.
I mean, I suppose I haven't seen it. So I think it's unlikely because the octopus is extremely similar to us. So that suggests a common origin to me. That I suppose the counter argument you could advance would be there's only one way to do life. So you could say that actually, given because the laws of physics and chemistry are the same everywhere. So maybe DNA is the only way to do it. So that's the way it gets done.
Which is why they're so similar to us.
Yeah, so
although so alien as well.
Yeah, they're not though. You know, that's the thing about an octopus. That's why I'm surprised about it, because they're not that alien. They're very similar.
Well, they're in their abilities. I mean, their ability to transform their outer texture and their color almost instantaneously.
Oh, yeah.
I mean, they have incredible camouflage abilities that really don't exist in the mammalian world.
Yeah, but on a cellular level, you look at an octopus cell under a microscope, and you wouldn't be able to tell the difference between an octopus cell and a human cell.
So the only way that would make sense is if all life comes from basically the same kind of building blocks and it just varies depending upon the conditions and where it takes place.
I'm guessing, but yes, that must be the only way you could sustain that, given that they're so similar to us, because they really are, biochemically, that's the only way it can be done, given the building block, the toolkit, the laws of nature and the elements and so on that we have in our universe.
We have so many different life forms on our planet, but if we found anything that's remotely similar to what we have here on Earth on another planet, it would be such an incredible discovery. Like if we found a frog on the moon, I mean, the world would stop, right?
I'd be very surprised if we found a frog on the moon.
But I mean, if we found anything anywhere that is in any way similar, an insect on Mars.
Well, this is, I mean, as I say, it'd be micro. I think it'd be single-celled things. Remember, I mean, you mentioned the Cambrian explosion. So that is what we do know about Earth is that although life began, let's say, 3.8 billion years ago, it wasn't until around 600 million years ago or so, or maybe at most 700, that you see any complex multicellular organisms at all. So for something like 3 billion years, it was single-celled alone. And that's one of the reasons why I would guess, if I had to guess, I would say that microbes would be common because life began very quickly on Earth. And I wouldn't be surprised if we find it on Mars. But complex life, multicellular life, insects, plants, intelligence, I would guess would be very rare because it took so long on Earth to get there. And it was just slime. About 3 billion years of slime. It was that was it.
And what happened? How did it go from slime to giraffes?
And it did it very quickly once it got going. Yeah. And it's one of the great unsolved mysteries in biology. That one thing that is true is that we seem to be all complex creatures. Seem to be we're called eukaryotes, right? Which is cells with a cell nucleus and all that kind of stuff. And they look like they're the merger between two simpler life forms, bacteria, and a thing called an archaean. So it looks like somewhere in 2 billion years ago, whatever it was, in some ocean, the bacterium cell got inside the archaean and survived as a symbiotic organism, essentially, and then somehow, unbelievably, managed to reproduce and replicate in that configuration. And that does seem to be the origin of all complex multicellular life on Earth. So it's called the fateful encounter hypothesis. And if that's true, then it's just a bit of luck. And it happened once, right? And that's why we're here.
Now, when
blind luck.
Consider, like, how many billion Earth-like planets did you say exist just in our solar system alone?
In the galaxy, 20 billion, something like that. So 1 in 10 stars.
So the odds of complex life out of our incredibly fortunate situation, but the odds of that occurring on any of these billions of other planets that exist?
We don't know, but let's say the Earth let's say it was on the fortunate side. So we're talking about, give or take, 4 billion years, right, from the origin of life to now. and we have a civilization now, and we've had it. Our species has been around, what, 250,000 years or something? So it's just now, basically. So let's say 4 billion is on the fortunate side. Let's say that it was double that, or triple that on the average. Suddenly, that's the age of the universe, right? And that's a third of the age of the universe it took. So how many of those worlds have been stable for 3 or 4 billion years? That's quite a tall order, actually. It looks like our solar system might be quite unusual in that respect, because the planet's got to remain stable in a stable orbit. The stars got to remain stable, at least in our solar system. Large moon stabilizes. Jupiter plays a big role.
Takes the asteroids. Sucks them in.
So, and that, there's a theory called the Grand Tack theory, which is, so it's very hard to explain the evolution of our solar system. So when you do computer models of solar systems, you don't tend to get 4 rocky planets too close to the sun and 4 big gas giants further out. And one of the current best theories, and I say this because it shows you how lucky we might be, is that Jupiter, they tend to form these big gas giants and migrate inwards towards the star. So in almost all the computer simulations, just because you've got this big gas giant orbiting in all the dust around the star, they tend to drop inwards. And it looks like Jupiter did that. So it looks like it formed and came in almost to where Mars orbits today, and cleared out the region around Mars, actually, which is maybe the reason Mars is so small compared to the other, to Venus and Earth. But then Saturn was coming in as well. And in the computer models, the interaction between Jupiter and Saturn stops Jupiter coming in before it gets to the Earth. And they both get dragged out again. And so to where they are today.
Oh, wow.
And so that seems to be, it's one of the best theories for the evolution of our solar system. So what are the chances? The chances of that are so minuscule, tiny. So that's the thing I think about these rocky planets. In order to get a civilization on them, I guess you need quite unusual solar systems, and that would be a guess. And you need quite unusual stability on the planet for billions of years. And that's why I think we might be quite lucky.
And how does Bode's law work? Bode's law is a method of detecting, if you look at the mass of a planet, you can accurately detect how much mass and the size of a neighboring planet.
I think, wasn't it just the positions of the orbits, I think.
Right, where it is.
Yeah. And it's one thing that is true about our solar system is that if you get the computer simulations, you can't put more planets in. So if you try and put more planets in, it becomes unstable very quickly. So
the mass of, like, if you measure Mars, you can accurately depict where the next planet close to it would be?
It was. I mean, it was. That's what was done. Was it 17th century or something? I can't remember. It was long. Yeah, and it was just one of those things where you notice a pattern.
Right. They were just trying to figure out what the patterns
were. Yeah, so it's just a pattern, which is, there's nothing to that really. Other than to say that most simulations of the solar system, if you put other planets in, they tend to get thrown out by gravitational interactions. So there is a sense in which our solar system has got as much stuff in it as it could have. So the planets are nicely spaced. And you're right, given the mass of them, that depends on how close another planet can be before the interaction goes wrong and it gets thrown out into galactic space or something, because planets do that. We know that planets get thrown out of solar systems by gravitational interactions. So, it points to the fact that solar systems are not stable over long periods of time. They're not like clockwork things. They're not like Newtonian clockwork and it just goes on forever. They're not like that. They evolve, and planets can shift orbits and change. And we know, if you look at the surface of the moon, for example, it's covered in craters. And that was caused, they all seem to hit about the same time. And it's about 3.8 billion years ago or so. And that's called the late heavy bombardment. So we know that if you look at cratering rates on Mars and on the moon, it all seemed to happen in this, not all, but a big peak around that time. And that seems to be correlated with Neptune moving outwards in the solar system and into the Kuiper Belt, basically, or towards the Kuiper Belt, and causing all sorts of havoc, and everything comes into the inner solar system. So those things happen. But it didn't happen when life was established on the Earth.
So it's all extremely old stuff these shifting took. But how long has the solar system been in this particularly stable situation that's in now?
It's since about 3.8 billion years ago. So if it had been unstable at any point since then we likely wouldn't be here.
Right. Do you think that it's possible? Do you ever entertain the idea that it's possible that we are the only intelligent life in the known universe?
I tend to restrict myself to the galaxy. Right. So I do think it's possible that at the moment there's one civilization in the Milky Way. Wow. And that's us. And I think that's important, actually. And it goes back to what I was saying at the start about the astronomy and cosmology being part of the framework within which you have to think. If you're looking for meaning, or you're looking for how we should behave even politically, that has a bearing to me. I mean, imagine that we're the only place where there is intelligence in this galaxy. And how should we behave? Right. Should we actually, notwithstanding the fact that we're tiny and fragile things and insignificant physically, should we consider ourselves extremely valuable in that respect? Because there's nowhere else where, I would go as far as to say there would be nowhere else where meaning exists in the Milky Way.
Meaning.
Because meaning is one of those things that scientists don't talk about very much, although Richard Feynman, one of my great heroes, did talk about it. There's a quote where he says, "What is the meaning of it all?" It's a great essay called The Value of Science. And so what is self-evidently true is that meaning exists here because it means something to us. So that's kind of an obvious statement. Life means something to you and me, and so meaning exists. But I think it is a local and temporary phenomenon. I think it emerges. Meaning emerges from configurations of atoms, which is what we are. We are simply that. We're nothing more than that. We're very, very rare configurations of atoms, I think. And so that means that we are, if you go all the way down that line of logic, we are the only island of meaning in the galaxy.
The meaning only to ourselves.
Yeah.
It means something to us because we're the only ones who can grasp the concept. And we are finite. We are a finite organism. We have this temporary existence while we're here. And to us, there is meaning.
Yeah. And I don't know any other way to define it.
Right.
So I'll define it like that.
Yes.
I don't think there's global, otherwise you have to believe there's some kind of global meaning and that's a God type thing. And I don't think I think it's more wonderful and more challenging to us because we have to take responsibility for it to say we should operate such that we are it in this galaxy. There's nothing else. I'm sure there are other civilizations out there in the universe because there are 2 trillion galaxies. I just can't believe this hasn't happened in other places. The question is how often does it happen and how widely spaced are the civilizations? And I think they're very widely spaced, and I think there may be 1 or 2 per galaxy on the average. But that, as you said, what you said it beautifully. That what else can we think?
Right.
And what else do you want? I mean, I think what it says is you have to take responsibility for all those things, those spiritual things that you think about and the emotional things you think about. You are responsible for that. You are that, right? That whatever that is. It exists in you, and it will only exist for a short amount of time. And so, make the best of it would be my view.
It's so unbelievably compelling, though, to consider the idea that somewhere out there, there's another civilization that may be even more advanced than us. And this thought of it is just so attractive. It's incredible.
There should be, if civilizations are common, or even slightly common, then there should be civilizations ahead of us.
Yes.
Because there's been so much time.
But wouldn't you want to see what that's like?
Yeah, I mean, we've been around.
So compelling.
You imagine the timescales. We've been around as a civilization. Let's give it, say, 40,000 years. I don't know how long our civilization's been around. Let's say that. The galaxy is pretty much as old as the universe. It's 13 billion years worth of time. So the idea that there are no civilizations arose, 100 million years ago, 200 million years ago, 1 billion years ago. And imagine what they'd be like if they'd survived. I mean, we've been around, we've had science for, let's say, since Newton or Copernicus, 500 years at most. And look what we've done. We've gone beyond the solar system with Voyager. We've walked on the moon. We're about to go to Mars, I would think. So we're about to begin colonizing our own solar system. So we've done that in 500 years. So imagine a million years in the future. So it's one of the arguments often used to say there aren't any civilizations out there in the galaxy. It's called the Fermi paradox. Because if you imagine a civilization that's a million years ahead of us, they should have written their presence across the sky by now. You should see them. I mean, you'll see us. If we survive a million years into the future, actually even a few thousand years into the future, we will be exploring the galaxy. We will have spacecraft that are going to other stars. We will be doing it. So our signature will become visible, I'm sure, if we last into the medium term.
Would we choose to not do that? Here's my thought on that is uncontacted tribes. Like, do you know about the gentleman who was the missionary who visited North Sentinel Island and was killed by the natives? North Sentinel Island, which is a really unusual place because they branched off from Africa 60,000 years ago, and they've been living on this one small island the size of Manhattan. And as well as we know, there's only about 39 of them left, somewhere around there. Yeah. And we're not supposed to contact them. Like, people are not supposed, we're supposed to like leave them alone. And they're a rare tribe. When they find them in the Amazon, the uncontacted tribes, our initial instinct is back off, leave them alone, leave them alone. Do you think that perhaps the universe, like if there is a civilization that's 1,000,000 times more advanced than us and been around here for, millions of years of life as opposed to 250,000, why would they let us know? Like, would they look at us dropping bombs on each other and polluting the ocean and sucking all the fish out and putting clouds into the skies of dirt and particles? And why would they, like, look at these crude monkeys. Look at that. They're so far beyond where they need to be before they could join the galactic civilization network or whatever.
It is true. It's an argument that there is an argument as well that technology so advanced would be difficult for us to detect. I mean, we tend to think of, when you say written across the sky, I suppose it's true. I'm thinking of starships and things like Star Wars, right? Big energy things that you can see the signature of. But actually, it may be that the civilization just becomes a nano civilization, tiny little nanobot, because that's more efficient. It's a better way to do things. So it's possible, I suppose, that there are space probes all over the place that are so small and are so efficient and use so little energy that we just don't see them. I suppose that is possible.
My other thought is that where we are headed, it seems to me that there's some sort of a strange symbiosis that's taking place. There's a strange connection that we have to electronics and ultimately to an artificial creation, artificial intelligence, whatever you want to call it, artificial life, something that's created by carbon-based beings, cellular beings that isn't cellular, but also acts like life. That this may be the future of life, that we are so connected to the idea of flesh and blood and bone, but maybe this is just a temporary situation until we transition, or if not us transition, till it surpasses us, and this is the next stage of life. But this stage has no need for all the human and biological reward systems that are in place that made sure that we survive, whether it's ego or fear or emotions. No need for that. That it will just exist and maintain its equilibrium as this new form of life, and that this is the future of life in the universe, and that we'll get there. Maybe it'll only be 100, 200 years from now, but that's what exists all throughout the cosmos. So there's no need to peacock. There's no need to show our signal in the sky, and that it just exists in this form. Yeah,
I agree. I wouldn't be surprised either. Yeah, so that's the counter argument to this Fermi paradox argument that I talked about. Well, exactly as you've just said, that basically you evolve to a point very rapidly where you just don't create a signature.
Yes,
and you don't really get involved, as you said. Maybe
it just maintains.
Watch.
Like, well, it has no, there's no motivation, right? Like, it doesn't, our motivations are so weird, right? We have these biological motivations to survive and, there's motivations to conquer and to innovate and to spread our genes and to move into new territories. But if you didn't have biology, if you existed completely from man-made materials or from materials found on Earth, and that this new form of life is created out of that, it wouldn't have those unless you programmed them. And why would you do that?
It is interesting, isn't it, to because we don't know what consciousness is, right? So it's often called a hard problem in science. We don't know. So it's a good question whether you can build, let's say you want to build a self-replicating machine, which is what you're talking about, and something that can go and maybe go to the moon or Mars and replicate itself and then carry on, which is a living thing, I suppose.
Yes.
Does it have to have a sufficient level of intelligence that it actually is conscious? And all these things that we talked about, this word meaning that we used earlier, that we all understand but can't define, is that a emergent property that has to emerge if you've got something that's intelligent enough to replicate itself and live and, as you said, be the... I don't know the answer, but it's worth considering that this thing, emotion, meaning, love and fear and all those things, are just the things that happen when you are intelligent.
Right.
I don't know the answer to that, but it could possibly be.
And does consciousness have to have a local origin? Like, does it have to come from a thing? Like, if you think about cellular communication, if you're in England and you send me a video from your phone and it reaches my phone, it's getting to me through space. It's going through the sky. It's like literally from a device not connected by any wires or anything. It's coming to me. If there's a possibility to create some sort of global intelligence through electronics that's non-local, if one piece of it falls off, it just repairs itself or figures itself out. But it's the same consciousness existing on a global scale through some sort of an electronic network. That instead of the idea that you and I have, that Brian and Joe you have your mind, I have my mind, and we exist as intelligent beings separate from each other. But instead of that all of it is connected, and that all of it is something that we can't even conceive of because our brains are too crude, like trying to explain to, Australopithecus what a satellite is.
Yeah. I mean, yes. I mean, if you think about our brains, they are ultimately, what are they? They're just a distributed network of cells connected by neurons. And I mean, they're very complicated, but they are a colony of things that are autonomous in a sense and are communicating with each other. So I don't see why you can't scale that up in principle. I mean, I should just the caveat is always that we don't know about this.
Yeah.
It's just not understood.
Well, I think there's something weird happening.
It's physical, though. I'm damn sure it's physical. I'm damn sure that there's nothing going on in my head other than what is allowed by the laws of nature as we understand them.
So eliminating woo, you mean? The idea of a soul being some sort of a divine thing that's inside the housing of the body.
Yeah, I mean, I would say we can rule that out, actually. I've argued in the past.
How do you rule it out?
I've argued we can rule that out in the following manner. So here's my arm, right? So it's made of electrons and protons and neutrons. And if I have a soul in there, something that we don't understand, but it's a different kind of energy or whatever it is that we don't have in physics at the moment, it interacts with matter because I'm moving my hand around. So whatever it is, it's something that interacts very strongly with matter. But if you look at the history of particle physics in particular, which is the study of matter, we spent decades making high precision measurements of how matter behaves and interacts. And we look, for example, for a fifth force of nature. So we know 4 forces: the gravity, the 2 nuclear forces called the weak and strong nuclear forces, and electromagnetism. And that's what we know exists. And we look for another one with ultra high precision, and we don't see any evidence of it. So I would claim that we know how matter interacts at these energies, so room temperature now, these energies, we know how matter interacts very precisely. And so if you want to suggest there's something else that interacts with matter strongly, then I would say that it's ruled out. I would go as far as say it is ruled out by experiment, or at least it is extremely subtle, and you would have to jump through a lot of hoops to come up with a theory of some stuff that we wouldn't have seen when we've observed how matter interacts, that is present in our bodies. And presumably, if you believe in the soul, you want it to exist outside when you die. You still want the thing to be there, and you might believe in ghosts and things like that. I mean, look at a ghost. I mean, it is something that carries the imprint of you. Presumably, it looks like you, right? So that means that it interacts strongly with the matter that is you, because it carries a pattern. If it carries a pattern, it carries information. If it carries information, there has to be an energy source that allows that information to persist and the pattern to persist, and so on. So again, you end up with a theory that is postulating something. It interacts with light, because if you think a ghost is the soul, then it's something that people see sometimes. So that means it interacts with light. But we know how light interacts, and we've ruled out anything but the most subtle further interaction that we haven't seen. So I claim, and I started off as a joke, this actually. I wrote it in an Infinite Monkey Cage book, this radio show that I do. But it ended up, when I'd written it down, I thought, actually, that it makes sense. And I read something similar, actually. I think Sean Carroll, I don't know if you've had Sean on the show.
Yes, a couple times.
He's said something the same. I think in the book that he wrote, The Big Picture, I think he has a similar argument, actually. So it's occurred to him as well. It's roughly the same argument.
So if you... So this energy that's interacting with matter, even if you're not moving at all, if you're just thinking, it's interacting with the matter that encompasses your mind or your brain or your nerves or your neurons.
Yeah.
It's something in there that's interacting with matter, whether you like it or not. So even just a simple thought process or a dream is still something that's interacting with matter.
Yeah. Well, obviously, because it's your will, isn't it, in that sense?
Yes.
So when you move, it's presumably
right.
moving.
But even if you're not moving, the idea, like you're saying, your body's interacting with matter as you're moving your arm. But even if you're not moving, if you're just thinking and you're completely still, which is not totally possible because your heart's beating and you're breathing and all that stuff. But if somehow or another you were able to isolate just the thoughts themselves are still interacting with matter because they're interacting with the brain itself.
Yeah.
So there's something in there.
Yeah, there's something that interacts with the physical structure of your body. And I would say there isn't. So that's...
The woo-woo version is that the brain itself and the body, the physical, the spiritual self, you are merely an antenna that's tuning into the great consciousness of the universe.
But why... But then you have to answer we know what we're made of. Yeah. So we know how those particles behave and interact.
Right.
So why do the particles not in any way interact with that stuff? Because we interact. We don't. If that's true, we don't only just interact with it. We interact extremely strongly with it. We're interacting with it now.
Yeah.
Every movement I make is an interaction between that and
every
the matter
thought you
in my
have.
body. Yeah.
Yes.
Well, everything. If I move my fingers around, everything that I'm doing is an interaction between that stuff and me. So it's a very strong interaction with matter, but we don't see it in all our precision measurements. Well, the answer for that, the answer is because it's not there.
The answer is Jesus, and you can't measure God.
That may be an answer, but the point is, as we talked about earlier with absolute space, if you can't measure it, it's not there.
Right. But for whatever reason, for people, there is some incredible motivation to find a divine something or another. There's something greater than this physical being. There's something. What do you think that is? Like, what is that compulsion?
We've already sort of talked a bit about it. I think it goes to the heart of this question of what it means to be human. So I would say that being human, the answer, right, it's not, I don't have the answer to the meaning of it all, but an answer would be we are small, finite beings, right, which are just clusters of atoms, as we said before, that are very rare, but we understand roughly how they came to be. And we have a limited amount of time, not actually unfortunately, but because of the laws of nature. The laws of nature forbid us to be immortal. Immortality is ruled out by the laws of physics. But also, actually, what's interesting about if you look at the basic physics of the universe, going from the Big Bang to where we are today, then the physics is driven by the fact that the universe began in an extremely ordered state. So it was a very highly ordered system. And it is tending towards a more disordered system at the moment. And that's called the Second Law of Thermodynamics. And it's that basic common sense thing that things go to shit, right? That's basically it's the Second Law of Thermodynamics. What we strongly suspect, and I would say no, is that in that process of going from order to disorder, complexity emerges naturally for a brief period of time. So it's a natural part of the evolution of the universe that you get a period in time when there's complexity in the universe. So stars and planets and galaxies and life and civilizations. But they exist because the universe is decaying, not in spite of the fact the universe is decaying. So our existence in that sort of picture is necessarily finite and necessarily time limited. And it is a remarkable thing that complexity has got so far that there are things in the universe that can think and feel and explore it. And I think that is the answer. If you want an answer to the meaning of it all, it's that you are part of the universe. Because of the way the laws of nature work, you are allowed to exist, but you're allowed to exist for a temporary or for a small amount of time in a possibly infinite universe.
One of the biggest mind-blowing moments, I think, of my limited comprehension of what it means to be a living being was when I found out that carbon and all the stuff that makes us has to come out of a dying star.
Yeah.
Like that alone, that there's this very strange cycle of these enormous fireballs that forge the material that makes Brian Cox.
Yeah.
Like what? That one alone, that there is some strange loop of biological life that comes from stars, which is like the most elemental thing that we can observe. We see these things in the sky. We see the sun in the sky. It's this all-powerful ball of fire. Yeah. And that is where the building blocks for a person come from.
I know. And they will be from the carbon atoms in our body. That you're right, they all got made in stars because there's none of it at the Big Bang. There's only hydrogen and helium, tiny bit of lithium to be precise, but nothing else. And so it was all made in stars. And it's probably from different stars. You know, the atoms in your body, they're not all from one star that cooked it and then died. There'll be a mixture of stuff from many stars in your body now. And I agree with you. What more do you want? You know, when I see people who go, I want more than that. I want more. You know, there must be more to it. What do you mean? The ingredients in our bodies were assembled in the hearts of long dead stars over billions of years, and have assembled themselves spontaneously into temporary structures that can think and feel and explore. And then those structures will decay away again at some point, and in the very far future, there'll be no structures left. So there we are. We exist in this little window when we can observe this magnificent universe. Why do you want any more?
Well, it's so, I think to people, I think a lot of people aren't aware of all the information, right? And then I think on top of it, for some people, it's so overwhelming.
Yeah.
This concept of 13.8 billion years of everything to get to this point that we're at right now, it's so overwhelming that they want to simplify it. Yeah. They want to put it into some sort of a fable structure, something where it's something that's very common and similar and familiar.
Yeah, I agree, but I think that's the journey that we go on. The real treasure, I think, is in that journey of trying to face the incomprehensible.
Yes.
It's in that realization that it's almost impossible to believe that we exist. Right?
Yes, right.
But that's a wonderful thing.
Yeah.
And I think that's what I think you miss out. I think if you decide to simplify it because you don't want to face that, you don't want to face the infinity that's out there in front of us, and you don't want to face those stories, as you said, that you look at your finger and its ingredients was cooked in multiple stars over billions of years. That's to me a joyous and powerful thing to think about.
Yes.
And I think you're missing out if you don't want to face that.
Well, I think the distribution of information has changed so radically over the last couple hundred years, and particularly over the last 20, that you're seeing these trends now where more people are inclined to abandon a lot of the, even if you remain religious or you keep a thought or a belief in a higher power, people are more inclined to entertain these concepts of science and to take in the understanding of what has been observed and documented and written about among scholars and academics. And there's more people accepting that. If you look at the number of agnostic people now as opposed to 20, 30 years ago, it's rising, it's changing. And I think there's also, because of you and because of Neil deGrasse Tyson and Sean Carroll and all these other people that are public intellectuals that are discussing this kind of stuff, people like myself have a far greater understanding of this than I think people did 30, 40 years ago. Yeah. And that trend is continuing, I think, in a very good direction.
Yeah. I mean, what we should say is that science, we don't know all the answers. So we don't know where the laws of nature came from. We don't know why the universe began in the way that it did, if indeed it had a beginning. So we don't know why the Big Bang was very, very highly ordered, which is ultimately, as Sean Carroll, actually, you mentioned him, often points out, and he's right, that the whole difference, the only difference between the past and the future, the so-called arrow of time, is that in the past the universe was really ordered, and it's getting more disordered. And that's that necessary state of order at the start of the universe, which is really the reason that we exist. That's the reason, because the universe began in a particular form. We don't know why that was. So we will probably find out at some point, and it'll be something to do with the laws of nature. But so I'm always careful. I don't want to. Science can sometimes sound arrogant, right? It can sometimes sound like it's the discipline of saying to people, well, you're not right.
Yes, yes.
And it's not the discipline of saying you're not right. It's saying this is what we found out.
Yeah.
So I like to say that it provides a framework within which, if you want to philosophize or you want to do theology or you want to ask these deep questions about why we're here, you have to operate within that framework because it's just an observational framework.
Yes.
So everything we've said is stuff we've discovered. It's not stuff that someone made up, right? We understand nuclear physics. We can build nuclear reactors, for example. So we understand the physics of stars. So we understand that the stars built the carbon and oxygen, and we know how they did it. We can see it because, as I said before, if you look far out into the universe, you're looking way back in time. And as you look back in time, you see less carbon and less oxygen. So we have a direct observation that in the earliest universe, there wasn't any because we can see it. And now we see that there is some, and we know how it was made. So I think it's important to be humble when you're talking about science. And you're not saying this is the way that it is. I mean, you are in a sense, but it's not able to answer ultimate questions at the moment. It's not able to answer even whether the universe had a beginning or not. We don't even know that. And I gave a talk to I was asked to give a talk to some bishops in the UK about cosmology, and I said, yeah, that'll be great fun. And so I went and gave him this talk, and at the end I said, I've got some questions. So if the universe is eternal, and it might not have had a beginning, if it's eternal, what place is there for a creator? That's a good question.
Right.
They didn't have an answer, of course, right?
An eternal creator.
But I think that it might be eternal, and we might discover that. So we don't know at the moment, but we might. So I think my point is that these other human design. It's very natural to religion's a natural thing, right? People, you see it all across the world in all different cultures. But I think that in the 21st century, religion needs to operate within that framework. If it's going to operate, there are still great mysteries, and it is appropriate to think about what it means to be human. And I've given you my view of what it means, but I don't think the problem comes when your theology or your philosophy forces you to deny some facts, some measurement. Now, these things are measurements. We're not saying, it's not my opinion the universe is 13.8 billion years old. We measured it. It's like having an opinion between the distance from LA to New York. No, you can't have an opinion on that.
Right.
We know what it is. And it's the same,
right.
It's like, these things, that people say the Earth's flat or whatever. So it isn't, and we've measured it. So it's just stop it. But that doesn't mean you can't be spiritual and you can't be religious. I would say it doesn't mean you can't believe in God or gods. That's not ruled out by science. But some stuff's ruled out.
Well, I love the way you communicate this because it takes into consideration human nature. And, I love Dawkins. He's fantastic. I think he's very, very, very valuable. But he likes to call people idiots. And the problem with that is people go, fuck you, you're an idiot. It is a natural inclination when you insult people to argue back and to sort of dig their heels in.
Yeah.
And you don't do that. And I think that's very important. And I think that a guy like Dawkins just gets frustrated from all these years of debates with people who are uneducated or saying ridiculous things. And he's a bit of a curmudgeon, and he seems to be softening as he's getting older.
Well, he's an evolutionary biologist,
yes.
And that's the front line in
yes.
some sense, isn't it?
Yes, it is.
The thing about particle physics is that you don't get a lot of shit because people don't understand what you're talking about. Whereas I think evolutionary biology is right there. So I understand his frustration.
Oh, I do too.
Having said that, I've kind of softened a bit over the years, actually, because now I think at this point, both in the US actually and in Britain and in some other countries, we are at a point, you've sort of alluded to it, where everybody's angry. There's a lot of anger, and a lot of it's justified, by the way. We could talk about that, income inequality and all those things. So there's justified anger. But it seems to me that there are people of goodwill who need to band together to diffuse the anger in our societies. Otherwise, we won't have countries like the United States.
Yes.
There's the United States because it's united and everybody, you've got the American flag there. There's a sense of belonging and identity and togetherness in a country which you've got to preserve. And so I've stopped actually picking. I used to, for example, quite enjoy picking fights with Deepak Chopra on Twitter. And it's just fun.
Me
and it's
too.
a laugh, and you just do it.
Pick
And
some fights with him too.
he says some crazy stuff, and but I've stopped doing it. Going, well, but relative to some of the other people,
right?
He's someone who means well.
Yes.
I don't agree with virtually anything he says. However, he's a well-meaning person, and so I've started trying to seek common ground. Now that's why I for example, gave a talk to the bishops that asked me to come. Yeah, I don't agree with them on the framework, their theological framework, but they mean well, most of them.
Yeah.
So I think seeking consensus and diffusing anger, as you said, it is incumbent on all of us, especially people like us who have a public voice. We need to diffuse some of this anger because otherwise it will consume everyone.
Yes, I've tried very hard to evolve in that respect and just get better at communicating ideas and get better at understanding how people receive those ideas. And I think it's easy to get lazy and to insult and to
and it's fun and it's funny. It's funny.
Yeah. Well, especially me. I mean, I'm a comedian. It's part of what I do is insult people.
Yeah.
But I do it
funny.
for humor. I want to entertain people. That's the whole idea behind it. But I think in terms of discussing ideas, especially that are so personal to people, like religion, I've re-examined the way I interpret these ideas and the way I talk about these things.
Yeah. It's interesting. I did a BBC program ages ago. I was asked to do it on this thing called the Wreath Lectures at the BBC that the BBC have done since 1952, I think it was, and Robert Oppenheimer did them in 1953. And it's fascinating. You can get the transcripts online; they're free, and you can get one recording of the 5. They taped over the other 4. Can you believe it?
Wow!
So they erased them. because they wanted the tape for something else.
No.
It's just unbelievable. But one of them exists of Oppenheimer giving these lectures.
Oh my God! How could they do that?
I know, but you can read it. It's just
they
insane.
taped over. Can you buy more tapes?
And Bertrand Russell did them. They taped over them.
They taped over Bertrand Russell's.
I know.
Oh my God!
It's just bizarre because tape was so expensive. But he talks.
That's crazy.
Yeah, but it's brilliant. It's called Science and the Common Understanding. And they weren't very well received because they thought he was going to talk about the Manhattan Project. So they thought he was going to talk about the atom bomb, because he ran it basically, but he didn't. He talked about how thinking like a scientist, which means thinking in the way that nature forces you to think, can be valuable in other areas. And that's an insight in itself. The great thing, the unique thing about science is nature forces you to think like that. You can't have an opinion. You can't have an opinion about gravity. Right, if you jump out a building, you're going to hit the ground. That's it.
Yeah.
Doesn't matter what your opinion is. And he said, so if you think about, for example, quantum mechanics, so sometimes you think of a particle like an electron. Sometimes it's a point-like object. It behaves like a little billiard ball thing, a pool ball that bounces around. But sometimes it behaves like an extended thing, like a wavy thing. And nature forces you to hold both ideas in your head at the same time in order to get a complete picture of the object, a description of an electron. And he said that's the valuable thing about quantum mechanics. Unless you're doing electronics or inventing lasers, you don't need to know this stuff. But if you want to learn how to think, it's valuable to be forced to hold different ideas in your head at the same time. It's really teaching you not to be an absolutist. It's really teaching you. The example he uses is, because I think he had problems with McCarthy and all those things, didn't he? So you think he's writing in the 50s. So he said you can be a communist, which in his definition would be that you think the needs of the many outweigh the needs of the few, right? So society is all that matters. Or you could be a libertarian, right, on the far conservative end, where you think that the individual is the only thing that matters, and that's it. But actually, of course, to have a functioning society, you need a mixture of the two. And we can weight it one way or the other, but you need to hold both ideas in your head at the same time. And he said that's one of the most valuable things about science, because it forces you into modes of thought that are valuable. And that's what we're talking about here. We're talking about absolute positions are always just a blinkered sort of subset of what's actually happening. You can't understand the world by being an extremist.
Yeah.
You've got to hold all these views in your head.
Well, that I find that so often on this podcast, because I talk with people I agree with and disagree with, and I always try to put myself in the head of the person that I disagree with. I always try to figure out how they're coming to those conclusions or where they're coming from.
Yeah.
And I think it's so important to not be married to ideas. Like, I had a conversation with someone about this, and they said, like, sometimes you change your opinions a lot. I go, yeah, I do. I do.
As if it's a bad thing.
Like I'm flip-flopping. I'm not a politician. Like, I'm not flip-flopping. I'm thinking. Yeah. I'm not sure. I'm not sure. Like, I will have one opinion on a thing, whether it's a controversial thing like universal basic income. I'll change my mind 100% in 2 weeks.
Yeah.
And I'll go, no. Now I think it's probably a good idea.
Yeah.
And then I'll go back and forth. No. People need it's as cruel as it seems. They need motivation. And I don't know. I bounce around with these things. Yeah. But I've tried really hard as I've gotten older to have less absolute opinions.
Yeah. Yeah, Richard Feynman, another great physicist, wrote a similar essay at a similar time to Oppenheimer. And he also worked on the Manhattan Project. And it's called The Value of Science. And I think that was 1955. And they both shared, actually, a surprise, I think, that they were still alive. Because they thought that the power they'd given to the politicians, the atom bomb, would destroy everything. They didn't think that the political system would control it, and it did. So that's an remarkable thing.
Yeah.
We're still here. But in that essay, he said that the most valuable thing about science is the realization that we don't know. And he said in that statement, he calls science a satisfactory philosophy of ignorance, by the way. Wow. And he said in that statement is the open door, the open channel, he called it. So if we want to make progress, we have to understand that we don't know everything, and we have to leave things to future generations, and we can be uncertain and we can change our minds. And he said that it's a great last line. I can't remember exactly what he says, but he said it's something like, it's our duty as scientists to communicate the value of uncertainty and the value of freedom of thought to all future generations. That's the point. That's what freedom of thought means. Freedom of thought means the freedom to change your mind. And in fact, said that's what democracy is, if you think about it. Democracy is a trial and error system. So it's the admission that we don't know how to do it. Therefore, we'll change. Every 4 years, we'll change the president, or every 8 years, we'll change the president. Why? Because the president doesn't know how to do it. So someone better. There will be someone better that comes along, and then someone worse and someone better. Yeah. But it's a trial and error system. And he's right. And he's right that is the open door. That's the road to progress.
Well, certainly better than
humility.
Yeah. One of the things that I love so much about Bertrand Russell and about Feynman was how human they were. They were very human. I mean, Feynman liked to play the bongos, and he was chasing girls. And Bertrand Russell was addicted to tobacco. He would talk about how he wouldn't fly unless he could smoke. Like, he had to get us, was back when they had smoking sections on airplanes. And he had his pipe, and he just refused to fly without tobacco. He couldn't imagine being without tobacco. I'm like, that's so strange for such a brilliant guy to be addicted to such a gross thing.
Yeah, you're right, because I think these are people that found existence joyous, right? Yes. They wanted to know. They just wanted to know stuff.
Yeah.
They didn't want to know everything, because you can't know everything.
Right.
I suppose that's what, if you think about what the job of a scientist is, it's to stand on the edge of the known, because you're a research scientist. So if there's nothing to know, then you've got no job. Right. So you have to be naturally comfortable with not knowing. And if there's one thing I really do think, how do we begin to patch our countries back up again? One of the reasons, I think, in education is to teach people the value of uncertainty, of not knowing. It is not weak to not know. It's actually natural not to know.
And that's one of the problems with religion, is to say that you know when you do not, or to say that you have absolute truth and absolute knowledge of something when it can't really exist.
Yeah, I mean, history tells us, doesn't it, that you know, anyone who thinks they've got absolute knowledge causes trouble.
Yeah. Did you see Ex Machina?
Yeah.
Did you enjoy it?
Yes. I know Alex Garland, because he wrote Sunshine.
Oh, right. So that's right.
And 28 Days Later.
Yeah.
And
so that other new movie, the weird one, the Alien movie, he wrote that as well, right?
Oh God, what's it called?
Annihilation. Yes.
Yeah. It's got a great soundtrack.
Yeah. Are you scared of artificial life, artificial intelligence? Elon Musk scared the shit out of me.
Yeah.
When he talked about it. Like, he talks about it like we're in the opening scene of a science fiction movie where he's trying to warn people, and then they don't listen to the genius, and it goes south. Sort
of depends. I chaired a debate on this with the Royal Society in London a few weeks ago, and so it's true now at the moment. What people tend to be frightened of are general AIs, or AGI they call it, artificial general intelligence, which is like what we talked about earlier, a human-like capability thing.
Yes.
And we're miles away from that. We don't know how to do it. We haven't got them, and we're miles away. So at the moment, artificial intelligence is expert systems and very focused systems that do particular things. You can be scared of them in a limited economic sense because they're going to displace people's jobs. And actually, interestingly, in this panel discussion we had, it's going to be like what you might call middle-class jobs in the UK, so white-collar jobs. It's not actually
why people are interested in universal basic income, to sort of replace money that's going to be lost, because there will be no jobs for all these people. Otherwise, we have just a mass catastrophe.
Yeah, they're very good. Someone said that these systems, artificial intelligence systems at the moment, are very good at doing things like lawyers' work. So they're very good at reading contracts and things like that. So it's interesting because it's a revolution. It's not like the Industrial Revolution where it's manual labor that gets hit necessarily. This is kind of interesting because it hits that kind of intermediate level that usually escapes. So you're right. One of the answers is to tax. There was an example was a robot tax. So in a car factory, you say to the manufacturer, well, okay, you can have a robot, but you pay the robot the same as you pay a person. And then that money goes into funding universal basic income or something like that. So I think there's got to be an economic change because these systems will be there. But all the experts I spoke to agreed that the idea of a Terminator-style general intelligence taking over the world is miles away. And so whilst we might start thinking about the regulation, it's not going to happen soon, is the general point, I think. So I would disagree with him on that. I think it's too far in the future at the moment. I might be one of those people that's going, it's going to be all right.
Right.
And then my iPhone takes me out on the way to the airport.
Yeah.
That's the thing. I mean, it's our choice at the moment, isn't it? I mean, don't give your iPhone a laser,
Right.
for example. And it doesn't matter if it goes crazy and tries to take over the world. I know that's a bit facetious because he would say they could take over power grids and all that kind of stuff.
Yes.
I guess, but.
Well, it's these concepts that are really hard to visualize, like sort of Kurzweil's idea of the exponential increase of technology leading us to a point in the near future where you're going to be able to download your consciousness into a computer. You talk to computer experts, they're like, there's no way, we're miles away from that.
Yeah, or neuroscientists.
Yes.
Neuroscientists go,
no way. Yeah.
One brain cell, probably we can't.
But Kurzweil's convinced that what's going to happen is that as technology increases, it increases in this wildly exponential way where we really can't visualize it. We can't even imagine how much advancement will take place over 50 years. But in those 50 years, something's going to happen that radically changes our idea of what's possible. And I think Elon shares this idea as well, that it's going to sneak up on us so quickly that when it does go live, it'll be too late.
Yeah. I mean, it's worth putting the framework in place, I think, the regulatory framework. Even as you said, for the more realistic problem, which is people's jobs are going to get displaced.
Yes.
And there's a great... I was at a thing and someone said, I can't remember who it was, but they said that it was a politician, the job of the innovation system is to create jobs faster than it destroys them. So you've always got to remember that as a government and as regulators. If you're going to allow technologies into the marketplace that destroy people's jobs, it is your responsibility to find a way of replacing those jobs or compensating those people, as you said.
Well,
otherwise you get breakdowns, social
being
breakdown.
a human being, though, is that people need some meaning. Like just giving them income, I think, is just going to. I mean, it's just my speculation, but it's going to create mass despair. Even if you provide them with food and shelter, people need things to do. So there's going to be some sort of a demand to find meaning for people. Give them occupations. Give them something, some task. It seems to be one of the critical parts of being a person, is that we need things to do that we find meaning in. You know, like you were talking about, we're the only things that we know of that have meaning, that find meaning and share meaning and believe in that. We're going to need something like that. If universal basic income comes along, I don't think it's going to be enough to just feed people and house them. Yeah. They're going to want something to do. If a person is you're doing something for an occupation and this is your identity, and then all of a sudden that occupation becomes irrelevant because the computer does it faster, cheaper, quicker. These people are going to have this incredible feeling of despair and just not being valuable. Yeah.
I mean, the utopian sort of a version of this is that everybody gets to do what we're doing now, which is make a living sort of thinking and creating and all that kind of, so that's the utopian ideal, is you don't need to do the stuff, the job that you don't really want to do in the factory.
Right.
You can do the thing that humans are best at. But I agree, that's a very utopian view. Yeah. Does everybody want to do that, or does everybody have the mindset?
Well,
maybe
it'd be
it goes
great
back to education.
If everybody had an interest like that, if everybody went on to make pottery and painting and doing all these different things that they've always really wanted to do, and their needs are met by the universal basic income money that they receive every month. But boy, there's a lot of people I don't think have those desires or needs, and to sort of force that onto them at age 55 or whatever it's going to be. Yeah, seems to be very, very difficult.
Yeah,
yeah,
I agree. I agree.
Yeah,
it's a big challenge.
But I think that in concept, at least, it's inevitable that we do have some sort of an artificial intelligence that resembles us, or that resembles something like Ex Machina, if people choose to create that. I mean, choose to create it in our own image. But that's very godlike, isn't it? God created us in his own image.
Yeah. And again, I don't know. When I talk to people in the field, as you probably have, most of them say, don't know how to do it.
Yeah.
It's really,
right.
It's going to be miles away. So maybe I'm hiding my head in the sand a bit, but I don't think so. I think we'll know it when, I don't think anyone's going to do it accidentally.
Right.
So I don't think it's just suddenly going to be upon us. I think we will see ourselves acquiring that capability.
We'll see ourselves getting close.
We'll see those systems beginning to emerge, and then we'll think about it. I think
200 years ago, if you wanted a photograph of something, you want a picture of something, you had to draw it. I mean, there was no photography 200 years ago.
Yeah.
I mean, just think of that. It's almost inconceivable. No automobiles, no photography.
Yeah.
What was automobile? Maybe there was some sort of machines that drove people around, right? Something close. There was trains earlier than that, right? You go back 500 years, you have almost nothing.
Yeah.
It's crazy.
Oh, we've been quick.
It's so fast. It's so fast. I mean, and then what we're doing right now, there's people right now in their car that are streaming this. So they're in their car and they're listening as they're driving on the road. Maybe they have a Tesla. Maybe they have an electric car. They're driving down the road, streaming two people talking, where it's ones and zeros that are broken down into some audible form, and you can listen to it in your car. That is bananas.
Yeah, I agree. We've been quick.
So quick.
Well, think of the world. The internet. I mean, it's not long. I mean, I remember it being invented.
Yeah.
Well, certainly the web.
When did you get on?
So the web. Well, it was very early for me because I was in doing particle physics, and of course the web comes from CERN, the www bit.
Right.
So it's certainly in the early 90s I was involved in that, in the university environment with email and all that kind of stuff. So I don't know when it kind of didn't really. You could have a web browser that just the only sites that were there were NASA, and I think NASA had one of the early sites, and CERN. There's very little else.
When did you become involved with CERN?
So that would be, I started doing particle physics in 95.
And when did the Large Hadron Collider go live?
That was, I remember it was 2007, I think it was, or 2008. It's so long ago that I can't remember. It's about 10 years ago. But it started up, and then we had a problem with it, and then it took a while to fix. So it hasn't been taking data that long, but it's a tremendously successful thing now, and it's operating beyond its design capabilities. It's quite incredible.
It's so stunning,
it's
like as a physical thing. That this, I mean, how large is it? How large is the loop?
It's 27 kilometers, so what's that, about 16 miles?
16 miles, and it's a circular, sort of a building. Yeah.
Well, it's a big tube. I mean, you think basically it's mainly under France and partly under Switzerland. And it accelerates protons around in a circle, both ways. One beam goes one way, one goes the other way, and they go around 11,000 times a second. So that's very close to the speed of light, 99.999999% the speed of light.
Wow.
And then we cross the beams and collide the particles, and in those collisions, you're recreating the conditions that were present less than a billionth of a second after the Big Bang. So we know that physics. So going back, what you said about the carbon and the oxygen, we can trace that story back way beyond the time when there were protons and neutrons to when there were quarks and gluons around, and go all the way back, and the Higgs-boson doing its thing back then. And so we can see all that physics in the lab. So that's why we have a lot of confidence in that story.
It's so fascinating that they were able to talk someone into funding that they got a bunch of people together, and that you were able to explain to politicians and regular people what you're trying to do. It's
a great example of how you get something done. So it was the 50s when CERN was established. I think it was 53 or 54. Can't quite remember. It's something like that. And it was built out from the Second World War. So you have Europe at the end of the war. And it was realized that the only way forward for Europe was collaboration, to rebuild the scientific base, and for peaceful purposes. And so CERN was set up as an international collaboration in Europe initially, with that political ideal that it would explore nature, just for freely and for peace, for peaceful means, peaceful reasons. And so that was the politics was right. So it was set up by international treaty so that the member states are bound together by a treaty. And they pay a small amount, relatively small amount each, into CERN every year, which is a percentage of their GDP. And that's the money they use to do the experiments and build the accelerators. So it's very hard to get out of it. And you wouldn't really want to, because it's a small amount of money per country. And CERN doesn't get extra money to build things. It just takes its money and basically saves up and plans itself. But because it's got a regular stream of money, it can do it. So it can say, we're going to build this machine, and it will take 8 years, because that's how much money we've got, and we'll build it in 8 years, and we know how much money we've got, so we can do it. And it's a lesson. I mean, the reason that the US collider, the SSC, failed is because it's the problem you have in the US with the funding system, as you've seen in the last few weeks, is that it's very arbitrary, and it's open to political maneuvering, and things can be shut down and CERN is not like that. CERN has got a guaranteed stream of funding, small, from each country, and so you can do these projects.
And the one in the U.S., that was during the Clinton administration? Is that what it was?
Yeah, it was was it Clinton? It was closed down by Congress on a very slim vote, and it was in Texas. So it was one of those things where you got states vying for money, and it was half built, and everyone was there, And the thing, it was bigger than the LHC, and it was closed down. So you waste a lot of money.
Is that a huge disappointment for the scientific community? Like, were people very hopeful that this was going to go live?
Yeah, it was being built. Yeah. So it dug half the tunnel.
What would it be able to do that the LHC couldn't do?
It was a higher energy accelerator than the LHC. So it would have discovered the Higgs particle first. Had it been running.
But the half-built part, is it useless now? Or can they sort of recharge it up again?
No, I think they filled it in. I think so. Oh. I mean, it was just half a tunnel, So that's the thing. You can do these wonderful things for not a lot of money if you just do it over many years and have stable funding and just commit to doing it.
The filling it in part is like...
And you look at CERN as well, and people ask me now, I think the UK pays about $100 million a year. That's what the UK pays in. And it's about the same for Germany, same for France, and so on. And so people say, what do we get for that? I mean, first of all, it's not... The whole budget of CERN is about the same as the budget of a medium-sized university. So it's not a lot. It's about $1 billion a year or something, which is what a university has. So it's not a lot in the scheme of things. What's it done, though? Well, we invented the World Wide Web, as we've just said. A lot of the medical imaging technology that we use comes from CERN. It's pioneered the use of these very high field magnets, which is what it needed. So it's engineering at the edge. And engineering at the edge generates spin-offs and expertise to get used in other fields. So there's cancer treatment, so-called hadron beam therapy. So if you've got a brain tumour now, it's quite likely that you'll have one of these targeted particle beam therapies, which is like very highly targeted sort of chemotherapy. It's not chemotherapy, it's just radiation that you can target in a beam into your head and attack the tumour. And those are particle accelerators. So most particle accelerators today are in hospitals and in medicine. Wow. But they came from doing particle physics. So the spin-offs of these big experiments at the edge of our capability are always immense, which is why they're worth funding at these very low levels. But it's not just the knowledge, it's the engineering expertise.
That there is a practical application for everyday life.
There always is. It's just finding out how to do hard things is usually useful, is the moral.
And it wasn't just the Higgs-boson particle that you guys had discovered. What is quark-gluon plasma?
Yeah, so that's shortly after the billionth of a second after the Big Bang. So you end up with a soup of quarks and gluons. So quarks are the building blocks of protons and neutrons, and gluons are the things that stick them together. So a proton has 2 up quarks and a down quark, and a neutron has 2 down quarks and an up quark, and so on. So they're the constituents, the protons and neutrons, which are the constituents of our atomic nuclei. So if you go to very high temperatures or high energies, then the protons and neutrons fall to bits. Then you end up with a soup of quarks and gluons, and that's a quark-gluon plasma.
And it's insanely dense, right?
Yeah, well, very high energy. So you get that. So we've been exploring that because we don't only collide protons together, we can collide lead nuclei together or silver nuclei together at the LHC. And that's when you make these kind of soups of nuclear matter, if you like, very hot nuclear matter, to explore that physics, to that nuclear physics.
Wow. And I was reading something about the weight of that stuff. That, like a sugar cube, like what is the actual weight?
Well, it depends how dense it is. So the thing I remember is the sugar cube of a neutron star material, which is, I don't know how many 100 million tons. I can't remember. It depends. But so I don't know with the quark gluon plasma. I don't know what number you're.
There was something. That was one of the things after the discovery. They were talking about the massive weight of quark gluon plasma, and almost incomprehensible.
Yeah. I don't know the number,
but something crazy.
Yeah.
Now, once these, you got something? Oh, here it is.
40 billion.
Oh my God! A cubic centimeter would weigh 40 billion tons.
Oh.
Good
cool.
Lord!
I didn't know that. I know David. I know David actually.
That's
University
so
of Birmingham. Yeah.
The densest matter created in the Big Bang machine. And what are they doing right now?
It's closed for engineering and upgrades.
Upgrades.
Yeah. I mean, one thing we're trying to do is, one of the things in particle physics is that you want as many collisions per second as you can generate. And we have a collision, we have what's called a bunch crossing at LHC. We can vary it, but it's something like 25 nanoseconds, depending on what. So it's really, we get a lot of collisions per second. And the more collisions per second you can get, the more chance you have of making interesting things like Higgs particles or whatever else may be out there waiting to be discovered. I mean, it's possible there are other particles out there that we haven't yet discovered that could be within the reach of the LHC.
And if this one that was in Texas had gotten built and it was more powerful than the LHC, you'd have even more opportunity to do something like that.
Yeah.
Now, when these things are created by these collisions, how long do they last?
Oh, fractions of a second. So the general rule in physics, in particle physics, is that the more massive it is and the more things it can decay into, the faster it'll do that. So basically, the heavy things decay into light things. And so the stable particles are things like electrons and some of the quarks. The up quarks and down quarks are stable things. But so everything tends to decay very fast. So we're talking billions of a second, fractions of.
And how are they
less than that?
How are they registering its existence? Like, what is being used to measure it?
So what you see, if you collide, at the LHC we collide protons together, and protons have got loads of stuff in them, loads of gluons and the quarks. So you get a big mess first of all. So most of it's a load of particles just spraying out, which you're not interested in. But sometimes when let's say a couple of the gluons bang together, and they can make something interesting, like a top quark or a Higgs particle.
What's a top quark?
A top quark's a very heavy. There's 6 quarks. So there's up and down, charm and strange, bottom and top.
Charm and strange?
Yeah. So strange was literally in the, what was it, the 50s when we discovered them. Someone said that's really strange. So it's a new kind of particle. So we have 6 quarks. They're in 3 families. So the up and down are one family, and then the charm and strange are another family, and the top and bottom are the third family. And so for some reason, so the only particles we need to make up you and me are up quarks, down quarks, and electrons. But for some reason, there are 2 further copies of those, which are identical in every way except they're heavier. So there's the charm and the strange quark, and a heavy electron called a muon, and then there's the top and the bottom quark, and another heavy electron called a tau, and that's it. So there's this weird pattern that we don't understand. So it seems like you only needed the first family to build a universe,
right?
But for some reason, there are 2 copies.
Now,
and the heavy ones decay into the lighter ones is the point. So when you make them, they're not around very long. And just to answer your question, what happens is that when they decay, they throw their decay products out into our detector. So we take a photograph of the cascade of particles that comes from these heavier particles decaying, and the trick is to patch it all up to try and sort of work out what everything came from.
Wow. Now, when they find these unexpected particles, then what happens? Then there's the study of them. Then there's then everybody gets together and go, okay, what the hell is that?
Yeah.
What is that? And what do we do?
So we want to know with a Higgs particle, we know what it does, which is it gives mass to everything. So it's fundamentally the thing that gives mass to all the other things in the universe at the most fundamental level. So electrons, for example, and the up and down quarks, they get their mass from their interaction with the Higgs. That's why they're massive. That's another reason we exist. We go right back. We wouldn't exist if there wasn't mass in the universe. And the Higgs is ultimately responsible for that mass. I keep caveating it because then you get other sorts of mass that are generated, but the fundamental basic seed, as it were, is from the Higgs. So what we want to know is we want to know how that thing behaves, and so you want to study it. So you want to make a lot of them, so you can take a lot of pictures of it and study it a lot and see exactly how it does that. And so that's what we're doing. That's what we're engaged in at the moment. We're making high precision measurements of the way that particle behaves, so we can understand the laws of nature. I mean, that is the laws of nature. How are those particles behaving and what are they doing?
But it is possible that some new form of particle, something else, could be discovered.
Yeah,
that we don't know about yet.
Because we almost know that there are other particles out there in the universe.
We almost know?
So there's a thing called dark matter.
Yes.
So we look out into the universe and we see that there's a lot of stuff there that's interacting gravitationally, but is not interacting strongly with the matter out of which we are made and the stars are made. So it's almost certain that that's some form of particle, that fits beautifully. And we see lots of different observations, the way galaxies rotate and interact, and even that oldest light in the universe, the so-called cosmic microwave background radiation, we see the signature of that stuff in that light as well. So we think that there's some other particle out there. And to be honest, we thought we would have detected it, I think, at LHC. We have lots of theories called supersymmetric theories that make predictions for all sorts of different particles that would interact weakly with normal matter. And I think it's broadly seen as a surprise that we haven't seen them at LHC. So that just may well mean that either they're a bit too massive, so we need more energy to make them, and we just haven't quite got enough. Or we're not making enough of them often enough to see them, which is one of the reasons we're upgrading the LHC. So we also look for them, by the way, directly. So we have experiments under mountains. We bury them under mountains so the cosmic rays from space don't interfere with them. And we're looking for the rare occasions when these dark matter particles bump into the particles of matter in the detector. So because the idea would be this room's full of them. I mean, the galaxy is swimming with dark matter as far as we can tell, but it interacts very weakly with this matter, so it doesn't bump into us very often. So we're looking for the direct detection of it, and we're looking to make those particles at LHC.
So it's everywhere, but it doesn't interact with us.
Very weakly. So it interacts through gravity, and the archetypal particle that's everywhere that doesn't interact strongly is a neutrino. So we do know about neutrinos. We've detected those. And there are something like 60 billion per centimetre squared per second passing through your head now from the sun. So they get made in nuclear reactions in the sun. But they go straight through your head and then actually straight through the Earth, pretty much. Occasionally one of them bumps into something. And we can detect those because there are so many of them going through. But we only detect, I don't know, 1 or 2 a day.
And the idea is that dark matter encompasses an enormous percentage of the universe.
Yes, it's 5 times as much matter as dark matter than is normal matter. And the number is 25% of the universe. So roughly speaking, about 5% of the universe is normal matter, stars and gas.
25% is dark matter.
Yeah, so 5 is normal matter, about 25 is dark matter, and about 70 is dark energy.
That's the other thing I was
going
to ask you about.
Yeah.
Yeah. So what the hell's that?
Don't know. Know what it does. So again, we talked about Einstein's theory earlier. So Einstein's theory, which works spectacularly well, says that if you put stuff into the universe, as we said before, then it warps and deforms and stretches. And it very precisely tells you, given the stuff that you put in it, how much does it stretch. and how does it stretch? And the measurement we have is how it's stretching. So we observe, the thing we observe is how the universe is expanding and how that expansion rate is changing and how it's changed over time. So we have very precise measurements of that. So then we can use the theory to tell us what's in it, given that we know how it's responding to that stuff. And that's how we discovered dark energy. So we notice that the universe's expansion rate is increasing. So the universe is accelerating in its expansion, which is exactly the opposite of what we thought. And this is in the 1990s that we discovered that. So we can work out what sort of stuff and how much of that stuff you need to put in the universe to make that happen. And that's where we get these numbers from.
Was there resistance to that when that was first proposed?
Yeah, I remember one of my friends at Brian Schmidt got the Nobel Prize for that. And I remember I talked to him and he said, he was a postdoc, I think, at the time, so a young researcher. And he was making measurements of supernova, the light from supernova explosions, which are so bright that you can see them, hundreds of millions, billions of light years away. And he noticed that if you look at the data, the light is stretched in the wrong way. So we look at the stretch of light as it travels across the universe, and the universe is expanding. It stretches the light, so it changes the colour. And he noticed that there was a discrepancy, which said that the expansion rate is speeding up. It's been speeding up for, I think it's something like 7 billion years or so. It's been speeding up. So he thought that he's done something wrong because so he checked it and checked it and checked it, and he couldn't find anything wrong. So he did what a good scientist does, which is he published it so that somebody else could find out what he'd done wrong. And he said that he thought it would be the end of his career. He thought it'd be a laughing stock, and he got the Nobel Prize because he was right. It is stretching.
Wow.
It's a great lesson. It means that if you're sure that you can't see what you've done wrong, then you publish it. It goes back to that thing about humility we talked about earlier. We're not trying to be right. We're trying to find out stuff. And so a good scientist will be really happy if they turn out to be wrong because they've learned something. Now, and it's good that he took that path because he got the Nobel Prize.
Now, when he received the Nobel Prize and this concept started being discussed, what was the initial reaction to it?
Well, it's interesting because it's allowed in Einstein's theory, and it was in Einstein's original theory. So it's got a name. It's called the cosmological constant, and that's it's just allowed in the equations. And Einstein actually introduced it initially because Einstein's equations strongly suggest that the universe is expanding or contracting and not just sat there. So even before we'd observed anything, Einstein had a theory that suggested that the universe is just not static. And actually it really strongly suggests that there's a beginning, right? So the theory itself on its own suggests that you can see that if the universe is stretching today, then it must have been smaller in the past, right? Everything must have been closer together, let's say that. There's a man actually called Georges Lemaitre who worked independently of Einstein, but at the same time in the early 1920s, before we even knew there were other galaxies beyond the Milky Way. And they noticed that the equations suggest the universe might be stretching. And so he wrote to Einstein and said, your theory suggests there was a day without a yesterday. Because he thought if everything's expanding now, then it must have been closer together in the past. And so there might be a time when it was all together. And he was a priest.
Wow.
So he's a Belgian priest. So I think, I wrote about this. Now it's kind of my interpretation of it. But I think that he was more predisposed to accept what the equations were telling him because a beginning, an origin for a priest is really a nice thing because it tells you the creation event.
Yeah.
And Einstein tried to dodge it and put this allowed term into his equation, which is almost the stretchy term, to say, well, if it's all kind of contracting or something, can I put something in to make it stretch a bit to balance it all out so it can be eternal? So, and you can't make it eternal that way. But he tried it. Then he took it out and called it his biggest blunder.
Taking it out was his biggest blunder.
No, he called putting it in his biggest blunder. Or at least some people think what he'd done was miss the prediction of the Big Bang, really. So by trying to fiddle around to have a static universe that's stable, He missed what the equations were screaming. His own theory was screaming to him, which is that, no, the universe expands or contracts. And he missed it, right? So I think that's probably what he meant by biggest blunder. But in any case, he took it out. And then later, in the 1990s, it turns out that, no, it's there. But it's really small. It's tiny, tiny effect. But it's still dominating the universe now. And it will dominate even more in the future. So we think that we're in a universe that will continue to expand, essentially doubling in size on a fixed timescale, which is about 20 billion years. So we think every 20 billion years into the future, forever, unless something happens, the universe will continue to expand and double in size.
Jeez.
And that's the dark energy that's driving that. But nobody knows what it is. It's one of the cutting-edge, massive problems in theoretical physics.
And what is being done to try to get a better grasp of what it is?
I mean, it's theoretical at the moment. I mean, we're making very precise observations of it.
Right.
And it looks like this constant. So it looks like it's basically a number, if you like, in Einstein's equations, and just really simple. So it looks like it's something that's maybe a property of space itself. Don't know. But it looks like a very simple thing that doesn't change over time and just stays there. So it requires theoretical advance as well. And so people are trying very hard to do that.
It's so crazy when you go from Galileo to modern theoretical physics that they're still in the midst of this understanding of what all this stuff is.
Yeah. I mean, these are fundamental and difficult problems. And we're talking about the origin and evolution of the universe.
Right.
That's what cosmology is. And it's also particle physics. I mean, the way that these things, this stuff, we keep talking about the stuff in the universe. That's what the LHC studies. It studies how the stuff behaves.
Right now, it's very theoretical, right? They're trying to wrap their minds around what this is and what the properties of it are. Do you envision a time where you can actually physically measure this and have a real clear understanding of what it is and what its properties are?
The dark energy. I don't know. I mean, for example, there are theories, which are probably not right, but they're not necessarily wrong either. There are theories that try to link it to the Higgs particle. So the Higgs particle, which we've discovered and can measure, has some properties that we think the dark energy would need. And also this inflation that I mentioned way back at the start of the universe, it has some of the properties that can do that as well. So, for example, there are people who try to link them. So we do have an observation of the Higgs, so we can study that. So are they linked? Don't know. But so it could be that we can study it, even though it's a very small, weak effect. It could be we have direct access. So it's great. I mean, these are big mysteries. That there's something really profound we don't understand about the way that stuff, in particular the Higgs, actually interacts with space and time. So very naively, the Higgs should blow the universe apart, just very naively. It's loads of energy in a very small amount of space, huge amounts of energy in the Higgs field. But it doesn't do anything apart from give mass to things. It doesn't directly affect space. But everything else that you put in space directly affects it. So, there are kind of issues there that we don't, and it just says we don't get it. We don't get it yet.
It's just
and
so
dark energy is
amazing.
another one of those. They've probably linked. If I was to guess, I'd say there's some link there. There's something going on, and solving one of them might solve the other two: inflation, Higgs, dark energy, something.
How many people worldwide would you estimate are trying to grasp this and working on this?
It's a good question. I don't know. I mean, it's probably tens of thousands if you count all the people who work at CERN and the particle physicists and the theoretical physicists. It'd be tens of thousands.
Because it's so important for us to get an understanding of what's going on, but yet so outside of the grasp of most people, including me. Like, I'm listening to you talk about this, and I'm like, thank God there's people like you. Thank quarks. There's people like you out there that are doing this. But it's almost like you're speaking another language. It's so strange to me.
Well, it's very new stuff.
Yes.
I mean, even when I was at school, so when I was at university, we hadn't discovered the top quark. And we sort of knew it was there. We thought the Higgs might be there, but we had no idea whether it was, So we're moving, in my career, we're moving quite fast. And you're right. These are the most fundamental questions about why is the universe the way it is? And even possibly, why is there a universe, right? But we're away from that yet. But if we're ever going to answer that, it will be by doing stuff like this.
And this is all addressed in this live show that you're doing, this worldwide live show.
And certainly also the consequences of not the consequences of knowledge, but the cosmology is terrifying, as we started with. So I think as we've said, it raises questions. It makes vivid questions that we all have about, what are we doing here? Right?
Yes.
So I try, and I think this goes all the way back to me really being into Carl Sagan. He always used to try this. You try to link it to things that people think about naturally. And that's why people are fascinated by this stuff, because they do actually think about it. It might not be with the right names or the right words or the right facts even, but they're thinking about, how did I get here? How did I come to exist? What is the future? Do we have a future? What was our past? These are universal questions, I think.
Yeah, they certainly are. And the way you're doing this with your live show, you were saying that you have an enormous visual aspect to it as well.
We have we have the biggest screen we can get in every venue, and it's LED. It's one of the state-of-the-art modern LED screens. So they're like Lego, and you can build them. So you fill the venue with it. So, at Wembley Arena, then it's 30 meters wide or whatever, by 8 meters high. It's enormous.
You must have a huge crew carrying all this stuff around. Yeah, that's
like 16 or 18 people, and it's like a rock and roll show. And at some of the venues we're doing it in North America, in Canada, they're a bit smaller venues, but we just fill it with screen as much as we can get. And then the graphics, a lot of the graphics I have were done by D-Neg, who did Ex Machina, actually, and Interstellar.
Oh,
and
wow.
the reason I chose them, I rang them up and goes, please, will you do this? And they said, how much money have you got? And, because it's way lower than Chris Nolan.
Yeah.
And they did it. And they were really, they just liked the idea of these messages and these ideas. So they used the software that they'd used for Interstellar to create images of black holes.
Wow.
And they used general relativity. They coded it into their graphics software. So they can ray trace light around black holes. And you can move the camera around the black hole, and it traces the way all the light moves around it. So if you remember those amazing, the Gargantua, the black hole in Interstellar, that's a simulation. It's not an artist's impression. It's a simulation of what Einstein's theory tells us a black hole will look like. And so I can use that to talk about what happens when you fall into a black hole. What would you see watching someone fall in? And you can explain all that using Einstein's theory. The idea that it's kind of a well-known idea, it's a bizarre idea that if I was to fall into a black hole and you were watching, you'd never see me fall in. You'd see time slow down. My time slow down as you watch me. So in the end, I'd just slow down and slow down and slow down. And then I'd get frozen on the event horizon and just fade away as an image, a reddening image on the event horizon. So time passes at different rates as you move close to the black hole and far away, because space and time are distorted by the mass of the black hole. And so I talk about all that, but I talk about all that with this incredible image, which we had. It's so high resolution, by the way, that it was higher resolution than they used for Interstellar, because my screen's so big. So we need a special machine to play it. You can buy the most expensive Mac Pro in the world, and it will not play this stuff. So I love that. From a geek perspective, it's brilliant. You have to have a special video player to play the damn thing.
So it's just like a series of CPUs all attached together in some sort of a supercomputer?
Yeah, it's one of those. It's one of the big sort of visualization graphics things. But these files are like, they're like 20 gig video files.
Wow.
Because there's so many pixels. The pixel resolution, this is really geeky, isn't it? The pixel resolution is 6,400 by 1536.
Is that impressive,
my
Jamie?
Screens.
So it's like 16K, right?
It's a lot.
Something like that.
Yeah.
It's big. Yeah, it's really big.
It's a lot. They're huge files.
Are you coming to Los
around.
Angeles with this?
Yeah.
When?
Yeah, at the Montalban Theatre in May, the end of May.
I'm there. If
Yeah.
I'm here.
Oh, there it is. Oh, yeah, no, you got to come.
okay.
24th of May.
Oh, you're in San Diego as well?
San Diego,
San
San
Jose.
Jose.
I got to see one of these. I
Yeah,
got to go to one of these.
It's going to be great fun. And however much stuff we can fit into those
Look at the
theatres.
picture of you, too, you handsome devil. Look at that. Nice jacket on. Looking good.
So, yeah, someone gave me that, actually. I managed
That's
to, I managed
cool.
to
You
scrounge that or something.
But it's cool because you look like a cool guy. Like you're a cool guy with space behind you.
Yeah.
Wow, that's awesome, man. Well, listen, thank you so much for doing this. I really appreciate you. I appreciate
Loved
everything
it.
you're doing. It's awesome.
No, thank you. I always enjoy coming. I loved it last time. And people still talk about it when I was on last time. More people asked me about meeting you than virtually anybody else.
That's
honestly.
crazy.
They
Well,
always say,
get ready.
what's he like?
Because it's like 100 times more popular than it was back then. It's going to be very strange now. But thank you again. Really appreciate it. I can't wait to see your show. Thank you so much.
Thank you.
Thank you. Bye, everybody.